Hello, everybody. My name is Torsten Hoefler from ETH Zurich, and I'm joining you from wonderful Switzerland to talk about, or to introduce the tutorial Productive Parallel Programming in FPGA with High-Level Synthesis that I'll be holding together with my student Johannes Licht, who is actually doing the majority of the tutorial, and I'm just opening it. So let me get started right away to give you a little bit of the background. So yes, we are talking about productive parallel programming on FPGA with high-level synthesis. So the key here is high-level synthesis and productive parallel programming. But the second question may be, why do we care about FPGAs? Why do we care about hardware design or designing algorithms that are much closer to hardware? And for this, I want to introduce the changing landscape and the changing hardware constraints that we have, and together with the physics of computing. And we all know this diagram. We've seen it multiple times. It summarizes the development from the early 70s until basically today. And what we can see is that there has been a phase change for many of these curves around 2005, 2006, which is really the end of Dennard scaling, which means that with the shrinking feature size of transistors, the energy consumption of those devices does not shrink proportionally. So actually, it may go up, or it may at least stay constant with the shrinking feature size. So this creates various issues that led to the multi-core crisis in about 2007, 2008, where now we had more and more cores. And now, in addition to this, we are even watching the end of Moore's law. I would claim it's already dead. Some companies are still insisting that it's going. However, the price per transistor, at least in TSMC's process, is already increasing. So in my view, that basically means that Moore's law is dead because it's an economic argument. And now we need to use these increasingly expensive, or at least not price reducing transistors more efficiently in order to squeeze out the last bit of performance. So how do we do this? But let me first explain a little bit more how we scaled the last couple of decades, in the last 50 years, in fact, or 55 years nearly. So we started with relatively coarse-grained processes. And when I started my career, it was about 130 nanometers. Then I watched it go down. In fact, at the 45 nanometers, I was involved with AMD in Dresden, helping them to launch their process of high-K dielectrica together with high-performance computing simulations with a package called Abinit. And there we have a lot of data available, or very precise data available, what the energy consumption is to perform certain operations on a CPU. So for example, a 32-bit floating point addition is about 1 picojoule energy that is required. A multiplication is about 3. But now moving these two operands from a relatively small memory, like an L1 sized 8 kilobyte SRAM, takes already an order of magnitude more, 10 picojoules. Moving these two operands from a larger memory, like let's say an L2 memory, takes already 2 orders of magnitude more, 100 picojoule, and reading them from DRAM, so from dynamic random access memory, is now multiple orders of magnitude more expensive. So data movement is quite expensive. But then we continue the scaling down to 10 nanometers. People are even talking about 3 nanometers now. The question is, what is the fundamental limit? So one fundamental limit we can establish is, of course, the Landauer limit, which is the minimum energy required in order to create or remove 1 bit of entropy. So 10 to the minus 6 picojoule, 0.2 times 10 to the minus 6 picojoule, a very, very small number. In fact, we are many orders of magnitude, about a factor of a million away from this. So there's a huge gap. Then, of course, with the shrinkage, there may be quantum effects, quantum noise that we may not be able to overcome. But another limit that we are actually hitting way before this is the cost of electrical data movement. Because below these transistors are wires, and these wires are metal wires. And the loss of a metal wire is proportional to the resistancy of the wire, which is a constant for the specific metal, times the length, which is okay, chips are very small, divided by the cross-section area. And this is now the problem. As we shrink the chips, actually these wires have to be smaller because they have to still connect these transistors on top as we shrink the transistors. And this means that the loss is actually going up with the shrinking. And so this leads us to one of the major issues in achieving high performance in chips today. We need to worry about locality. Spatial locality, temporal locality, two concepts very familiar with, I'm sure, all of you, but also control locality. And that is a slightly different concept that gets relevant in the context of FPGAs that I'm going to explain in a couple of minutes. But if you're interested in general issues of locality, in high-performance computing systems, I can recommend this TPDS article by Didem Unat and folks. I've also contributed to it, that summarizes environments quite well. But now let me get a little bit more into the control locality and the real difference between FPGAs and CPUs. So if you take a normal load store of a Neumann-style CPU and we want to solve this equation x equals a plus b, we first start with a memory, of course, where we have a and b stored. We have an ALU that at the end executes these operations. We have registers that have no semantic properties, but of course are important for performing the computation on somewhat local memory. So we already see locality plays a role in computer architecture. We have a control block that orchestrates the overall computation, and we have a cache that is also improving performance but has no semantic properties. So we could compute right on memory, but registers and cache just make it faster. And then we have a data path and a control path here in red connecting all of those. So how does it work? The von Neumann architecture loads an instruction to the control logic from memory that instructs it to load A. Then it loads another instruction that is instructing to load B. Of course, it executes those instructions, then it loads an add instruction, then the ALU performs the calculation, writes it back into X, and then X is written back through another instruction to main memory. So if we now look at the actual energy consumption breakdown, where is most energy spent, we see that it's less than 5% here for the actual addition and really 95% overhead in register file access, iCache access, control logic, all of those things. And if we now look at the slightly different non-von Neumann architecture, there are many of those, but if we just look at the static data flow architecture, we could see that this bottleneck, this control bottleneck, was sometimes also called the von Neumann bottleneck, but that has different contexts, could actually be overcome with a specialized architecture. So here we have, again, these operands in memory. I'm choosing a slightly different, more complex equation even to show a multi-stage, not just a single stage. But then we instantiate two adders and one multiplier. And the interesting thing is now that we can have these registers where they belong. So we can add two input registers and one output register to each of those units that apply binary operations and connect them in the right way between the memory and those units. What this means is now that the data is flowing through this very specialized architecture. It does exactly this one function, but it's extremely efficient because you never have this access to larger random memories. You read it right from the memory where it comes from and write it to a specific location, which means that the energy per operation is only 1 to 3 picojoule because you have very little overhead, no control overhead because the control is in the structure of the computational unit, and none of these cache accesses and register file accesses here. So this is what we mean by control locality. This is really the how do we localize the control to the circuit at hand? And now you could argue that there are many ways to improve that control locality and reduce the control overhead. One relatively simple way is either using vector units, SIMD units, or SIMT units in GPUs, where the fundamental principle is that we have one control for many, many, many executions. So here in this example, one control controls these 10 arithmetic logical units. So you could now argue that there is a tenth of the control overhead, which is of course true, but then there is still one bottleneck, and this is going to be quickly becoming an Amdahl's bottleneck. These ALUs still access registers and cache, and they still have to load these operands from these relatively large units. While in that case here, the registers are localized to the specific execution units. So here we are still paying 10 picojoule or maybe 100 picojoule, depending on the size of those registers. And here we are paying 0.1 picojoule because these registers are specialized to the units and the data flow is very clear. So at the end, high performance computing is really a data management challenge. So and now with the FPGA architectures, we can move that data management challenge down to the circuit, down to the FPGA in a spatial programming manner that we believe is quite powerful. So to go a little bit further into an overview of what high performance computing offers in terms of programmability versus silicon efficiency. So we have the left side here, which is used today in modern supercomputers. So we have CPUs, GPUs, and hybrid systems that are software programmable. So they're of course reprogrammable at runtime, so they don't have specialized circuits, but they have specialized circuits to some domain. So high throughput computing in the GPU case, and low latency computing in the CPU case, and then of course hybrid to combine throughput and latency computing. But this is software programmable. Now we have two more device types, which is FPGAs and CGRAs that are already in the area of hardware, but they are reprogrammable at the field, so to say, to cite the FPGA. And then we have specialized ASICs, which is not included in our discussion here because these have very fixed functions. But unfortunately, this programmable hardware is somewhat hard to program, and we are only at the beginning of hardware support as well as software support for high performance computing. So, but like everything we're discussing, it is a data movement challenge. So at the end, we're increasing these different forms of locality that I mentioned, and this is really what this tutorial is about. So let me introduce a little bit more what a field programmable gate array is. Field programmable gate array is really in its simplest instantiation, just a lookup table. So here a lookup table has 2 input bits and 1 output bit. And of course, the state space of this lookup table, so the possible number of possible functions it can implement is now 4. So 2 to the number of inputs. So we can now, for each bit combination, define a specific output. It's really just a table, like if it sees 2 0 bits coming in, it produces a 0 bit on the output, 0 1 produces a 1 bit, and so on. Now we can, of course, make these LUTs bigger because binary LUTs are quite small. So for example, here we can have 5 input values. And again, we have a table that translates these input values to output values that can now implement any arbitrary function that is definable on bits because it's a full table. So now we take lots of these LUTs with 5 elements and we put this on a so-called slice on an FPGA. We add some additional, so with a LUT you could implement anything with a collection of LUTs. But of course it could be relatively inefficient. This is why these slices, they add additional functionality. For example, a carry bit that connects multiple slices, various multiplexers, various flip-flops for storing data, and many, many other units. So now we take those slices, we put them on the FPGA chip. That FPGA chip has now even more specialization. So it has many of these slices. It has, I mean, this is what the logic fabric is about, but it may also have different DSP blocks. So these are programmable processors that you can actually use to further specialize and improve the silicon efficiency. It usually also has memory blocks where you can load and store data from. And then, of course, it has an interface to the external world, transceivers, and of course, the management block for these transceivers like PCI Express or C6 or whatever protocol the FPGA is speaking to the external world. So it's a relatively complex device. It's a heterogeneous device, but at the fundamental core, it has these lookup tables and these programmable DSPs. And then there are 2 vendors today, so we can two large vendors, there are smaller ones as well, but the market is pretty much dominated by either Xilinx or Altera, which is now Intel, and producing these programmable devices. And now if we look at the FPGA landscape in the context of, let's say, a GPU, another accelerated architecture. So here we are comparing the Intel Stratix 10 with the UltraScale U250 and an A100, the latest NVIDIA GPU that came out. So you can see that these are in a slightly coarser process run. These FPGAs are usually running at a slightly lower frequency because, of course, you need to enable all these LUTs and you can apply less optimizations to your data path. They have a peak performance here, 10 teraflop, 5.5 teraflop, but more flexible than the Intel implementation in the Xilinx case, but then twice as much on the A100 because, of course, it's hardened silicon and thus much more efficient. Usually, also, these FPGAs have slightly less memory than the GPU, but they're much more specializable. So there I can specialize the data path. And this is really where the power comes from of those FPGAs. Also, the energy consumption is much, much, much lower. So there's a lot of hope that we could use these devices to implement more efficient computing. This is, in practice, is going to be extremely hard to do this. However, we believe that the next generations that are more trimmed towards HPC would be performing much better. So now the question is, what is the real efficiency? I've given you some very fuzzy insight here, going from a programmable unit, a software programmable unit, to a hardware reconfigurable unit. So the data path is somewhat closer. But of course, in order to design silicon that is hardware reconfigurable, we're losing something. But at the beginning, we can gain about a 100x, and this is also a very rough guess, so it's usually between 50 and 100x efficiency by expressing these algorithms as a data flow model. So efficiency in terms of units or compute or connectivity. Unfortunately, to go from this fixed machine here to a fully reconfigurable machine, we are losing a factor of 10 to 20 in silicon efficiency. So now we are down to a factor of 10 in theory up here, of 5 to 10 that we can gain. And this is really what we are worrying about. Actually, this factor of 5 to 10, we can work on this area here, the 20x, because we don't have to express everything as a programmable unit, but we could use coarse-grained components. So for example, we could have fixed floating point units on that FPGA, which is what Intel does, that are then exactly as efficient as the fixed floating point units in a GPU. And we just replace the control path with reconfigurable logic. So we can get this loss. We can get that essentially arbitrarily far down, but now it's a trade-off between this programmable unit and this reconfigurable unit, which is quite a hard trade-off that we are not discussing in that tutorial here. And in fact, I believe many vendors are not fully understanding that trade-off. So there are many designs for very special purpose usually. So let's focus on the FPGAs we have today. And these are relatively powerful. So they have many hardened units. They're very close to CGRAs. And this is going to be fun to program those. So FPGAs is actually an interesting topic since a while. Many large-scale cloud vendors like Microsoft and Amazon have public FPGA offerings, so you can actually rent FPGAs in the cloud. Many use them to run infrastructure for the reasons that I just mentioned. Furthermore, there are many vendors that even try to push FPGAs into the high-performance computing market with varying success. So they haven't found widest adoption yet, but they're super interesting devices to look at, and they will be competitive if the trajectory continues. But as I mentioned, HPC uses GPUs, and the question is now, why are we mostly using GPUs as accelerators and not these exciting FPGAs for all the reasons I just told you? And the main reason that I hear and that I fully believe is productivity. CUDA is just a very nice language. OpenCL is a well-designed language, and there's a lot of support for GPU programming and executing applications on GPU, and the performance of GPUs is extremely good. I mean, the SIMD model is a very strong competitor for performance and efficiency and price. So it's going to be a hard battle for FPGAs if they want to reach more adoption in the HPC space. But as I mentioned, there is this potential factor of 10 or maybe even more to be gained with FPGAs. And this is what the cloud providers realized. So having very specialized implementations, very specialized codes leads to a significant benefit. And now the difference between scientific computing and the cloud is that you have an economy of scale in the cloud, that if you take 20 engineers, highly paid engineers, to engineer an FPGA firmware to run a specific application, it may be worth it because you may be running it on tens of millions of instances. While if you want to improve your, I don't know, conjugate gradient method for your little lab, then you may not be able to pay tens of engineers to do it. So it's pretty clear that you can do it. It's now less clear how much work it is. So there is really the issue of productivity that we have to address. And this is what we are addressing in this tutorial, teaching you to help you to achieve goals faster and more productively, and thus cheaper. The second issue that the hardware vendors are slowly addressing is hardware support. So FPGAs are now increasingly showing up with high bandwidth memory and native floating point units. That wasn't the case years ago. So they're actually specialized to high performance computing. So on the productivity side, well, as I mentioned, there are languages that are more productive. We'll be focusing on HLS languages here, but this generalizes to other languages. And Johannes will give you many examples that carry over between many of those languages, even though we are focusing on C++. Then the hardware support, as I mentioned, we have hardened floating point units in HBM available today on FPGAs. So talking about high-level synthesis, there is a lot going on in that field. So major vendors have high-level synthesis tools. Just a couple of weeks ago at FPL, Microsoft announced a new high-level synthesis framework that will hopefully be released relatively soon. So there is a lot of activity in that space. We cannot cover all of this. There are research environments. We are focusing here on high-level synthesis tools, mainly on Xilinx, but also on Intel, because they're relatively close. So to get to the focus, we really, you can draw the line between C++ and OpenCL. OpenCL is a language that has been designed for accelerating GPU workloads. So it's very close to the GPU architecture, which is not a 100% fit for FPGAs. And C++, of course, has been designed for programmers of traditional CPU-based systems to make things easier, like you have objects allowing you to express your semantic relationships. You have templates for more type-independent specification of programs, and you have many compile time constructs for performance and static type checking. These are all convenience functions for programmers. On the OpenCL side, we have very much hardware-specific constructs like workgroups, shared memory, and private memory constructs that are very close to GPUs, because GPUs have this shared memory, private memory, and they work with these warps and blocks that was abstracted into workgroups. And of course, the interaction with the host is done through kernels. And the intersection of those two is really the C language and pragmas. It's a very low-level intersection, unfortunately, but I'm very sure that in the very near future, we will lift this abstraction to be more convenient. But today, for that particular tutorial that we are giving, we are focusing on the C language and a little bit of C++ and these HLS pragmas to make your code fast. Furthermore, we do not, we kind of discard all of the GPU-specific pieces of that side here. Because even if you read the documentation of Intel's OpenCL, they will tell you do not use these features, write very simple kernels. And the kernels are basically used for the device and host interaction. So how to launch a kernel on the device and how to copy memory inputs and outputs back and forth between the device and the CPU. So with that, I would like to close my introduction and give the word to my student Johannes, who will now do the actual tutorial and show you practical things, how to actually use it, how to install the software, how to run codes on these FPGAs and work with them in a productive manner. Thank you very much, and you can ask me questions offline.
So let's try that one more time. Now we should actually be able to talk. Excellent. Starting over. Welcome to the second part, this time with sound. I am coming to you live from Zurich, Switzerland with my pandemic beard. I hope everyone is managing things well over there. I know you've been having a busy time in America lately, and also to those of you from the rest of the world. So we decided to do this whole part live because, in my opinion, the most important thing about this tutorial setting is that we can interact. Unfortunately, this is a little tricky this year. So because of the format, you cannot speak to me directly. And perhaps more importantly, I cannot see your faces and gauge the confusion in them and see if I'm making any sense. So I implore you to please use the question format as much as possible. Essentially ask anything that's unclear. Let me know if something doesn't make sense. There is a delay, so I might have gone on a little bit before we get to it, but we will address anything that is asked, and I really ask for your help to help me gauge how we're doing by asking questions and using the discussion features on the platform. So I'll just leave this slide on for a little while. So the stuff I'll be talking about today, we've given this tutorial quite a few times. I think this is the 6th or 7th time we give it. And a bunch of the information that is in this tutorial, we've also condensed into a survey paper. The survey paper has been an archive for a while, and it's also going to appear in TPDS probably sometime early next year. But it's available here. So once you have watched the tutorial and you're interested in playing with these things, I recommend referring back to this paper for a more sort of structured way of all the things we're going to talk about and more. Throughout the tutorial, I'll go through a bunch of demos, a bunch of live coding demos. Everything I will be going through is on GitHub. These examples are also updated regularly to keep up with all the regular breaking changes in the FPGA tools, which there happen a lot. There is a virtual machine that you can use to actually run these things in emulation. This is a 60 gigabyte download, I believe. I actually don't recommend doing that. If you can download tools yourself to play with, using the virtual machine can be extremely slow. So if you can get the tools yourself when you want to play with this on your own. And for actually running in hardware, not everyone has an FPGA lying around. That's still sort of an exotic thing. Nimbix has a trial where you can use some of the newest Xilinx boards. Put the link here, so in case you want to try to run stuff in hardware, this could be a good place to start. And I also just want to mention the Xilinx University program is a very generous institution that gives out licenses and hardware if you have a good purpose in your research. So if you're in academia, I highly recommend talking to the Xilinx University program. That being said, we are not affiliated with Xilinx. We're not affiliated with Intel, meaning this tutorial will be about HPC aspect of HLS development. So that means that you will hear me talk bad about the tools if need be. I don't have any special interests, so also keep that in mind. Ask anything related to the actual practical aspect of working with these things. If you've ever heard anyone who work with FPGA tools, you might have heard that it's not always a pleasant experience. So everything we talk about here today is not about how to use a specific tool, but rather it's about how to develop HPC architectures with HLS, no matter if you're using the Xilinx toolchain, the Intel toolchain, or something entirely else. And I just put my email address in the bottom. So apart from the platform here on Cadmium, you can also reach me here for any reason. Okay, so without further ado, I'm gonna start with the technical content now, and basically we're gonna be technical for the rest of this tutorial. And now I didn't keep track of the time exactly how much we were delayed, but we'll try to do the break around the usual time and do a half hour break somewhere in between. So like I said, we're gonna go at this from the HPC point of view. So what we're going to be talking about today is if this is your FPGA board, so this is actually a screenshot taken from within one of the FPGA tools, then we want to take this thing and we want to just cram as much logic onto this thing as possible and compute something useful in every piece of logic every cycle. That is sort of the end goal. We're doing HPC and this is what we'll be working towards, and I'll try to give you all of the tools that we need to reach a point like this. But to start, I'll start from the very bottom and then we'll zoom out a little bit until we reach the level of abstraction that we'll maintain for the rest of the tutorial. So don't be worried if there's a little bit of hardware stuff now. We're gonna be zooming out to a high abstraction level in just a moment. So if we think about what happens on your device when you're doing some operation, if we start from a very simple thing here, let's say I want to add two numbers. Then what happens on the FPGA is if we zoom in here a little bit, there are a bunch of very fine-grained components. Torsten talked about them a moment ago. And when you're doing this computation, somewhere on your chip, so not in some central registry file, because now we're talking about distributed logic here, somewhere on your chip, you're going to have some data stored and some registers. These are flip-flops shown here. Then when we want to compute something, we will essentially push them through some kind of logic, usually lookup tables, but they can also be other components. And then the result will be pushed into some output register. And everything that we do here is essentially this data jumping from pipeline stage to pipeline stage, from registers to registers, through a bunch of logic, and thereby computing stuff, which should not come as a surprise to anyone. But when we're working with FPGAs, this is much closer to the level of abstraction we actually work with. So it's good to keep in mind that this is what we're programming at the very bottom of the toolchain. So we can view it from a slightly higher level of abstraction by thinking of it as this input stage, output stage, and then some logic in between, where this thing in the middle is one clock cycle. So this is actually how FPGAs are or / were traditionally programmed. So your HDL languages like VHDL, Verilog, System Verilog, they look something like this here on the left. So you essentially program the behavior of the circuit. That's why it's called behavioral programming. You say every time there's a clock cycle, we want to take the contents of A and B and put it into C. So we're programming on this cycle by cycle level. But what happens if we now take this little addition here and we say now it's a floating type instead? This is a picture of a patent of a floating point adder. And as you might be able to see, this is not something that we can do very trivially on an FPGA where the components are very low level. So if we look at this abstracted view again, we're still going to have some input and some output and some logic in between, but this logic is now a little bit too deep for us to just clock the circuit and get a result out. So what happens in practice is the same thing that will happen if you're working on a normal CPU or any other fixed architecture, which is that we have to break this into multiple pipeline stages so that we can maintain a relatively high clock speed and we don't have to push it through a lot of logic between every stage. So we take a big floating point adder. Now we're going to have the input registers and the output registers, but we're also going to have some transient registers in between where the intermediate result is sort of being propagated along. So each of these steps will be one cycle, and we now have another number here, which is the total number of cycles it will take for some input here to propagate through all these stages and reach the output. So this brings us to what our point of view will be now that we're talking about HLS. We're essentially going to take this thing on the right here and say this is now lump, which has a latency specification on it, which is the number of these intermediate stages inside of this piece of logic plus 1. So how many cycles does it take to propagate something through this pipeline? And say this is now our abstraction. So for the rest of this presentation, we're going to be talking about how to design and program these pipelines. And this is sort of the level of hardware understanding that is necessary to keep working with HLS and optimize these codes, because everything that we optimize and everything that we do to add parallelism and stuff to our codes will be in this pipeline level of abstraction. So we're going to be working with pipelines a lot, and I'm going to be saying the word pipeline probably 2,000 times for the next 2 hours, so get used to it. So when I draw it like this, it means that internally in this block, there are L-1 internal pipeline stages. And it's not that we have to greatly care about if there are 7, 8, or 9 of these stages, but they will be relevant for some of the things that we do, and I'll go over it from a performance point of view throughout the tutorial. Okay. So we're doing HPC. We need to talk about performance, and the very first thing that we should do here is have some sort of performance model so we actually know what we're optimizing for and how this thing works, because this is a different way of thinking about performance than we're used to. In particular, when we do HLS, we're going to be much more in the domain of clock cycles than in the domain of seconds. So the diagram here is sort of the evolution in time, except we're counting time in cycles. That is not to say that time to completion is not still an important metric. Of course it is. And ultimately, the performance we get out of this will depend on not just how many cycles, but also the frequency at which they're executed. So definitely cycles are not the full story. But in terms of most of the optimizations that we're going to do and most of the work we're going to do, we're going to operate on the cycle level and then possibly do some frequency related optimizations later. So this is a good diagram to keep in mind. Time is progressing on the x-axis here. So the time our program is executing is essentially clock cycles ticking along. And on the y-axis, I put different operations. So this essentially means a set of operands that we want to compute in our circuit. And this latency number that I drew before with the internal pipeline stages is this number here. So in terms of the time diagram, I have pumped one set of operands into my circuit, and the latency tells you how many cycles are going to pass before that one result has been computed and the result pops out on the other side. So this will be sort of one of the important components of the performance model. But let's add a little bit more logic here. So now we're gonna go back and use the example that Torsten showed in his slides to show you the difference between a fixed and a data flow architecture, where we have two additions, or rather an addition and a subtraction, followed by multiplication. So already here, you can implement this in multiple ways. So we're no longer operating with a single ALU where where operands are just pushed in and pulled out again. We now have a very wide range of choices of how to actually implement this, and I'll talk about some of them now to give you an idea of the kind of behavior that your HLS tool will do when you synthesize these things. So one way you could imagine implementing this is that you instantiate every operation that you're planning on doing as a dedicated piece of hardware. So we have two adders here. One is doing the add, the other is doing the subtraction. And then we have a multiplier afterward, and the operands are going to be fed into both the adders, and then both of the adders will produce a result, which is fed to the multiplication and eventually to the output. So this whole thing would now again have a latency number. Again, we can keep sort of zooming and considering now this is just another pipeline that consists of multiple stages, and this whole thing would now have a latency corresponding to the sum of these two, plus or minus maybe individual little stages in between, but sort of roughly this would be 13 cycles, 8 for the add and 5 for the mult, where we're taking the critical path through the circuit, of course. So we can zoom out a little bit again and say this is now just an add mult unit with a latency of 13. But there's another way we could do this. In some sense, you could think of this as the more ALU-like way, how you could imagine this as being executed on a CPU, which is you have a adder, a unit capable of doing this operation. You feed in the operands for one of your additions, and then the following cycle, you feed into operands for your other addition. For example, if you're optimizing a reduction in CPU code, you will typically do this with partial adders, which means you can feed multiple separate additions into your pipeline with no dependencies, and you would basically do this. So doing that means we would interleave these two different additions, and that would give you an extra +1 cycle for the time it takes for all these operands to propagate through the pipeline. So this whole thing, again, as just a pipeline, would now be increased from 13 cycles to 14 cycles. And again, we can zoom out a bit and say this whole thing is now just a block with a latency of 14 cycles. So this leads us to the other very important part of the performance model, which is initiation interval. And this is also a term that you're going to hear all the time if you get anywhere close to HLS programming and vendor documentation, because it's a very important concept when it comes to performance, and is something we'll be talking about a bunch today as well. It might also very quickly become your worst enemy once you've been working with HLS tools for a while. So we have this property called initiation interval. When using vendor tools, it will often be called II. When I'm putting it here in equations, I'll just write I, but II is sort of the more common way of talking about it. It stands for initiation interval. Also, as a non-native speaker, you might also hear me stumble over the word initiation interval occasionally, because it's not the easiest thing to say. So now we have to look at the difference between these two circuits to understand what this means. So on the left-hand side, we built the circuit so that all the 4 inputs to the circuit as a whole, so we had our plus and our minus and our multiplication. If we imagine that as a single circuit, then the left-hand side and the right-hand side implement that circuit, but in 2 different ways. The left-hand circuit implements it by accepting every operand that we need to compute this whole sequence of operations at the same time, and then we can propagate the result through that. Whereas the right side requires us to wait between inputting operands. So on the left-hand side, we had the latency of 13, but then we have this initiation interval of 1. And what that means is just that every cycle we can accept a new set of operands to the pipeline. And in order to actually implement that, well, we need to instantiate every piece of logic explicitly. So we have 2 additions and 1 multiplication here. On the right side, as I showed you, we only added an extra cycle of latency because we needed to wait one extra cycle before we could feed the other set of operands into the adder and essentially propagate that inside of the pipeline. But because we have to alternate between the first set of operands and the second set of operands, this means that we will have this initiation interval of 2 cycles now. So only every 2 cycles can we accept the full set of operands necessary to compute the whole circuit, so the whole sequence of computations. The good news is you would only need one add and one multiplier to compute this. The thing is, if we now look at this from a point of view where we're executing multiple operations, what this actually means is, on the left-hand side, every cycle we accept a new set of operands. And if we sort of continue doing that, it means that every cycle we will push 3 sets of operands through the pipeline, which means we're effectively computing 3 operations per cycle. On the right-hand side, we are alternating all the time. We do one set of operands, then the other set of operands, which effectively means that by the time that we have propagated some amount of operands through this circuit, we have only computed these 3 operations, still 3 operations, but we've only computed them every 2 cycles, which essentially means that this has halved our throughput. So there's sort of a few ways to think about this. The way I explained to you now is that essentially this initiation interval is the number of cycles before we can accept a new input into our circuit. And if you look at Intel documentation, if you've ever been messing with Intel intrinsics, this is what they call gap, essentially the same thing. Basically just how many cycles we have to wait before accepting new operands. But like I just showed now, it can also be seen as just the inverse throughput of the pipeline, because essentially the whole pipeline, if you look at it from a zoomed out perspective, this is how many cycles we have to wait before accepting new things, and this is also how it's sometimes referred to in the Intel documentation. And essentially, from our point of view, this will be the factor slowdown of your application. So that's the reason why we talk about this initiation interval a lot, and that's because this is going to be crucial for designing these pipelines and getting all this parallelism, is that we always have a circuit that can accept the maximum number of operands, which means having an initiation interval of 1. So like I said, this is something you're going to be hearing a lot in any context of HLS, is initiation intervals of 1. It's one of our holy grails. So if we go back to this diagram here, our performance model thing, we drew the latency as being this distance from a single set of operands entering to that set of operands coming out on the other side. And the initiation interval is then this quantity here. So how many cycles, so some measurement of time between accepting a new set of operands into the pipeline. But all of this doesn't really do anything and doesn't make sense if we don't actually have some loops. So obviously we need loops to actually perform any sort of meaningful computation, and if we didn't need loops, we probably didn't care about FPGAs in the first place. So now we have taken this computation that I've been talking about a bunch now and just stuck it inside a loop. And the way we now talk to the HLS tool is through these pragmas. And if you dislike pragmas, then you're like me. Unfortunately, this is how we're going to deal with it. So both Intel OpenCL and Vivado HLS, the Xilinx tool, they make a big deal out of essentially being C++/OpenCL compliant, but that means that there is no special syntax. So the only way you can get around not having special syntax is by shoving in pragmas, and that is what they did. So somehow we need to communicate to the tool that we're taking our imperative code and we want to build these pipelines. So this is going to be the first example of one of these pragmas, is that we can say we have this loop and we know we can build this circuit in a number of different ways, but the thing we can tell the tool is that we want this circuit to be executed in a pipeline with initiation interval of 1. So we're essentially, instead of saying this is how you should implement the circuit, we're saying this is the throughput requirements we want from a circuit. So in some sense, from an HPC developer's point of view, this makes a lot of sense. We're essentially telling the tool the performance we want rather than the specifics of how to implement stuff. And to some sense, that is also true. And one of the cool things about FPGAs, which is also one of the worst things, depending on how well things are going for you, is that you have quite direct control over what gets emitted. If you do software optimizations, you will know that in order to, let's say, optimize for a cache hierarchy, you don't really have any direct feedback of how it's going, except you see if your performance goes up and down, and you have no real guarantee to see why it went up and down without going and instrumenting a lot of different things and trying to draw some connections. So in the FPGA world, the connections are much more direct, but it also means that we have to deal with a lot more stuff than you will have on the CPU side. But we'll talk about that plenty. So now we're going to zoom out a little bit on this circuit again. Like before, we draw the latency, but now we also draw the initiation interval there. So these are the two important properties we need for our performance model, and then we can look at what is the performance of this whole thing. So one iteration of pushing something through this loop, so just let's say we're now executing this loop, we synthesize the hardware and we want to see how long it takes. Then executing one iteration would now take us 13 cycles, which is the latency of the circuit, plus one extra cycle for the one operand we want to push through our circuit. If we set our n to 10, so now we're executing 10 iterations, then we would spend the 13 cycles of the first operand who entered the pipeline until it propagated to the end, plus then waiting for the last 10 to fall out on the other side, so a total of 23 cycles. And in general, if you're pushing through n elements, then it's going to take you n plus 13 cycles. And as you can guess, the important thing here is that the latency number is just additive to the number of iterations that we're performing here. And this is a very important fact that we're going to be using to actually get performance later on, because this is a fact that keeps being true regardless of what we put in the body. So inside the body here, we had the plus, the minus, and the multiplication. And the plus and the minus multiplication, what that gave us was this latency of 13. But what I'm showing you here is that no matter what we put inside this loop, it only changes this constant number on the left, which is 13. And if you're doing HPC or doing anything performance interesting, which you are, because you would not bother with FPGAs if you weren't, your n will be large, which means you do not care about this 13. So keep this in mind. We pipeline our sections of code, and we do not pay performance-wise for whatever we put in there. So if you put 100 multiplications in there, it has the same runtime as putting one multiplication in there. So that's pretty cool, right? Now, essentially, we need to figure out how can we build some of these pipelines that have many multiplications in them and actually do some useful work. And this is what we'll be spending a lot of our time on now. So let's look at the other example here. I showed you this was another way we could implement the same effective computation here. And the way we could make our tool emit that, we cannot really do it directly, but we can tell it that we only need an initiation interval of 2. Let's just go along with that for a second. Then we could, again, compile this circuit and then get something else out. So zooming out here on the right, we would get a block now with a latency of 14, initiation interval of 2. And we could plug that into the performance model. We would have a similar situation as before, but now the runtime would go as follows. So for one iteration, you would have this latency of 14 that you have to pay, but then you would have to wait the 2 cycles for plugging in the one set of operands and the other set of operands. And for 10 iterations, you would have to do that 10 times. So you would have to pay 20 cycles for the different operands you have to put in. And in general, the right term here would now be 2n instead of n. And as you can probably imagine, this generalizes to this thing here. So the important thing being initiation interval is paid at every iteration. So latency we get for free whenever the number of iterations is large, which we essentially are just assuming it is when we're doing HPC-oriented workloads. We're going to be talking a little bit about what happens when you have cases where n can be small, but in the general case, we will have a lot of iterations we want to perform. So as long as we keep this initiation interval as low as possible, but generally just 1, then we will get the rest for free. Cool. So with this, I want to jump into the first code example and show you a little bit how this works with a tool. So I will just share a different screen. And I will please ask someone to shout at me if something is not visible, but I'll just carry on here. So here is a fresh clone of the Git repository that I linked you in the beginning. It's also in the handouts, and it contains a bunch of these example codes. Inside the example codes, you will see some subdirectories. The README contains essentially a brief summary of what I'm telling you now verbally anyway. So if you want to look at this later, especially if you've attended here and you remember a bit about what I said, then these README should help you sort of refresh what the point of these examples are and what you should be looking for. And the examples contain both Xilinx and Intel versions for some of them. For some of them, they don't, because the point of the examples is to show something that the Intel tools don't show you. There are upsides and downsides to both the Xilinx and Intel tools, which I will not go into right now, but for the purpose of this tutorial, we will use the Xilinx tool basically for pedagogical reasons, that we get some more information out that we can use to see and understand the performance model directly. So when you get this repository, this is all set up with CMake, so you basically just make an out of source build. I need to set a couple of parameters here. It should work in principle with any version of the tools, but no guarantees that it will always work with any version, because like I said, both FPGA vendors like to introduce lots of breaking changes all the time, so it's kind of hard to keep up, but we do our best. And inside of these build folders, we'll then have a bunch of build targets that we can use to show some of these things that I'll show you now. So let's jump into the first example. So this is essentially the code I've been showing on the slides, but stuck into a piece of HLS code. This is in Xilinx syntax, which means we do have C++ enabled. And basically I took this the little circuit we've been using so far, and I just stuck it in a loop, and I put it in a function and added a couple of extra lines. So we're taking 2 pieces of memory. This could come from wherever. And we do this operation on them. And just to make it non-trivial, these are different pieces of memory. It's not that we have to write the code like this. Just don't be scared. It's not that we have to do every array access on an explicit separate line, but I'm writing it this way just to make it very clear that when we are accessing memory, and why will become clear in a moment. But in principle, this could be either from DRAM or from some local memory. But we're taking these operands, and then we're computing this operation that we had before, and then we have this little pragma here that we can use to instruct the tool what our throughput requirements are for this thing. So there are now a bunch of build targets, and what I want to show you for this example is basically just what happens when we actually build this tool, and a little bit about what the tool outputs, to get an idea of how our code maps to this performance model that I've been babbling about for the past 10-15 minutes. So inside the example folder, there will be a make target that runs high-level synthesis. This now calls the Vivado HLS compiler and takes this thing and binds the C++ program into a hardware description language representation. Like I said earlier, this tutorial is not about the specifics of this tool, so I'm not going to go into great detail about how Vivado HLS works or how the Intel tools work. I'm going to focus on the performance aspect so we can move toward the high performance goal that I talked about in the beginning, and sort of focus on those aspects. And there are plenty of resources out there for the specifics of the tool. So let's start by focusing on what comes out here. There's a bunch of yada yada yada, but the important thing for what we just talked about is that there was a loop in here, and this loop was now pipelined by the tool. So we asked for an initiation interval of 1, and you can see here that it gave it a go, tried to pipeline the loop. It tried to get an initiation interval of 1, and it got an initiation interval of 1. And then there's a depth thing here. And the depth thing is a way of talking about this latency parameter that I mentioned before. These are the sort of things that will that can change names in the terminology depending on the vendors, but essentially these are the two parameters of the performance model that we've been talking about, the initiation interval and the latency. So that's one thing we can look at here. The other thing is it also emitted a bunch of hardware that we can see here explicitly. There are there's a floating point adder, there's a floating point multiplier, and there's a floating point subtractor, which is essentially just adder. So these three different modules that we talked about. And this thing also emits a little report module. These on Xilinx, this is a little text file. In Intel, you get a sort of a full-blown HTML thing, but for the purpose of the tutorial, it's a little easier to look at the text files for now. And we can see some of these performance characteristics of the loop. So this specific line is why we've chosen Xilinx for the tutorial, because it's nice to see these numbers explicitly. I discovered that starting from the newest version, this has disappeared for our tutorial. So as I said, stuff changes with these tools all the time, but I used the version 19.2 for this to still work. But we basically get these numbers back. So we have this initiation interval that we targeted, the initiation interval that we actually achieved, how many times a loop is executed. So these 1024. I don't think I showed you up here that we've just defined the n to be 1024. It doesn't have to be hard-coded to write the hardware, but I'm hard-coding it so that we can get exact numbers here, which makes it a bit easier to talk about. So we have 1024 loop iterations. We have a latency of 10, which gives us a total number of not 1024 plus 10, but approximately that many clock cycles. A couple disappeared magically, but essentially what our performance model said, that we have the number of iterations that we're pushing through the pipeline plus this constant latency term at the end. So if you wanted to now compute the actual runtime of this circuit that you have designed here, you would take the number of cycles here and divide it by the frequency. And if we change this number here, so let's say we're doing 2048 cycles with semicolon, and we run this thing again. By the way, these examples will take progressively longer to compile as we progress throughout the tutorial. Blame Xilinx. And we open this report thing again. Then we now see the number of iterations of the loop has increased to 2048. The latency did not change because the content of the loop did not change. And the total number of cycles it takes to execute it is now, again, just the number of iterations that we put in plus the constant latency. So like what we would expect. So the other thing I want to show here was what happens if we do this. So bear with me for a second. There's not any particular reason why you would do this in practice, but it will become relevant. So let's say we want to explicitly have our latency to be, our initiation interval to be 2 instead of 1, and we run the synthesis again. And thank you, Nicholas, for posting the link to the GitHub examples again. They're also in the handout file there was, and there's also a link on our website. I will post that in a second. There are links to everything from there. So now I ran this again, and we can now see that according to the performance model, we still have these 2048 iterations that I said for the loop, but the initiation interval is now 2, which means the total number of cycles it takes to execute this is now 2 times 2048 plus our constant latency, which is now 4,000 cycles. So I know this might be sounding a bit trivial, but it's very important to understand how this works, that this performance model is you can observe directly in these reports what the runtime of your application will be. And this is maybe a bit cooler than it sounds, because if you design these circuits and you monitor these numbers that come out, you can really expect that this is the runtime of your circuit. So if I now take this, I compile it for hardware, I set n to a little bit more than 4,000 because otherwise it's very trivial. I set it to a very high number. The runtime of my circuit will literally be this number of cycles divided by the frequency, and you can measure it down to microseconds, notwithstanding indeterministic things, bandwidth bottlenecks, and so on. But it really gives you a very accurate number. And this is sort of a cool thing of the whole FPGA design thing, is that these numbers are accurate and very deterministic. Also, when you do benchmarking of FPGA programs, it's convenient for when you're writing papers because there's essentially no variance. You run it again, and it will produce exactly the same runtime as it did all the other times you ran it. Okay, so that was sort of to show you how this performance model is emitted by one of the tools, and just to play around with a little bit. And I welcome you to, after the tutorial, you can go and play around with this yourself. So let's jump back to the slides. I'll also just check the questions in a second to see if there's anything we should talk about. The tutorial example is running on Linux. So everything I'm showing you now here is technically running on a Linux machine over at the university. I'm sitting on a Windows machine, but yes, I've actually only ever used FPGA tools from Linux. I think in principle the Xilinx tools support Windows as well, and I assume the Intel ones too. But I'm running this through WSL right now and SSHing into another machine. But everything is set up to run on Linux. And I think that was all. Okay, so why do we worry so much? Now I've been going on and on about this initiation interval, but it seems very clear that it should be 1. So why don't we just set it to 1? There are a few reasons why it's not that simple. So there's a reason why I've been talking about this so much. There are a few situations where this might be done to you rather than by you. One is interface contention. So did I disappear from the stream? Oh, okay. I just noticed myself disappear for a moment. Okay, so there are some reasons why this might occur in practice. I can see this is also a question in the chat. Let me get back to the specific question in the chat in a second. So there are a few reasons why we might run into this. One is interface contention. So we're generating hardware now, which means that everything we access needs to be scheduled to be accessed on a cycle-by-cycle basis. So that means that if we have a fixed amount of hardware and we're accessing it more times in a single cycle, then the interface of that hardware cannot be wired up more than once. And this can give us issues that we cannot do this every cycle. We'll show you that in a second. The other very common situation is data dependencies, or rather loop carry dependencies. So if you're executing multiple loop cycles and something happening in one loop cycle depends on a result of something computed in a previous loop cycle, in particular any sort of reduction accumulation pattern, this can also give us issues with initiation interval, and I will talk about that later because you will definitely run into this in practice. And then there are a few situations where you might not actually need it. So adjusting it manually like I did just now, it's not something that you commonly do, but it does actually happen that you don't need to accept a result very often. For example, if you're doing a reduction pattern and the reduction pattern will emit a bunch of partial results every n cycles, then taking those partial results and summing them up might not have any high throughput requirements because it will be n cycles before we get the next set of partial outputs. So in certain situations, we're not interested in just throwing as much hardware at it as possible when we can actually take our time to compute something. But it's not super common, so it's not something you really need to worry about. Most cases, we just want to have this low initiation interval. So I'll start by discussing this top situation. It's a very common situation. It's a bit more common with Xilinx and Intel because in the meantime, Intel FPGAs have native floating point units, which means that certain accumulation patterns are actually supported natively. So some of these problems magically go away as long as you're working in 32-bit floating point on a fairly modern Intel platform. But unsilings will happen pretty much always, and as soon as you go to 64-bit or anything more exotic, it will come back. So in any case, this is an important thing to talk about. So let's start with the interface contention part. So here's an example of a common situation where you might have a initiation interval that's higher forced upon you. So in this case, we have a loop, a one-dimensional loop that we're trying to pipeline, and within that, we're trying to take the average of an array. So you can imagine this as being some average over a one-dimensional thing in an image application. This could be doing a blur filter or something like this. Here simplified to 1D for the sake of argument. And for that, we need to access multiple entries of this input array to actually do the blurring. So if you think about what this hardware would look like, you're basically taking a discrete piece of hardware, so an array that is somehow represented. It could be DRAM, it could be some on-chip memory that you're accessing, and you're trying to access it 3 times in a single cycle. Because what this pipeline pragma means is everything inside this loop needs to happen every clock cycle, and we cannot do that. So what we would actually get out of this is this could only be scheduled every 3 cycles, 1 cycle for the first access, 1 for the second, and 1 for the third. In practice, it could be even worse because each of these might result in separate requests to the DRAM controller, but we're not going to get into that right now. The good news is there's fast memory everywhere. And like I mentioned before, with the programmability of FPGAs, it's sort of the worst thing and the best thing about FPGAs at the same time is that we have to program everything ourselves. But the good thing is we get to program everything ourselves. And for any of you who've been struggling with trying to squeeze your code into 3 layers of cache hierarchy, you might know that implicit is not always a good thing for performance optimization. So if we look at our chip here, again, this is a snapshot from one of the FPGA tools. We have a bunch of different options here. The first is registers. I showed you this in the very first simple example that we could put our data in registers, and this is essentially what's happening when we're just pipelining our results and pushing some logic through the chip. But we also have better components for bulk storage. So either vendor has these RAM blocks, large storage components, relatively large, depending on your definition of large. So something like being able to store maybe 500 32-bit floats or something like this, which you can essentially use for storing bulk amounts of data, but on the chip. So really very close to your computation, you have this large amounts of storage where you can go and put stuff. And even more exotically, there are even other ways you can store data. It's not important right now, but even the logic units themselves can, in some instances, be used as storage. So lots of options for where we can put our results and essentially move our data closer to the computations, which is what we dream about as HPC programmers. Less data movement, less distance between your compute and your memory. Great. So going back to this example, what we had in the beginning was we take this array and we want to feed it to the loop. But now we want to access multiple parts of this array. So what can we do about it? So essentially what we could program is something like this. When we read in the first value, we feed it to the loop, but we also take it and we store it in a register and essentially propagate it along to the next iteration of the loop. So in the second stage, we could read out the value from that register, feed it back into the loop, and again, propagate it forward to the next iteration of the loop. And then finally, in the third stage, we can read the value from the second register and the first register and from the actual memory interface at the same time, and we'll have all 3 values fed to us at the same time. So I'm talking about stages here, but keep in mind that this is not temporal in the sense of they're executed one by one. All these stages would then be executed at the same time, but for different input operands that are currently propagating through the pipeline. And this is now a pattern that we need to translate into how we write our C++ or OpenCL code, so that these end up corresponding to these actual indices that we wanted, the I+1, the I, and the I-1. And if we can do that, we would be happy and be back to our initiation interval of 1. So with that, I'll jump into the second example, example 1. All right. So I will just jump out here. And again, I hope someone shouts at me if something is not visible. So the code I just showed you, I've now translated into this little thing here. It's almost the same as what I just showed you. I've just named it a simple 1D stencil because that's essentially what it is, and I've put a little bit of frame around it. And like before, I've taken these 3 axes and made them very explicit. Not because we have to write it in this way to work with FPGAs, but because I'm trying to make it very clear from seeing the code directly that we're accessing this 3 times. So then we're doing the computation and we're writing this out. So now let's see what happens when we try to build this, or synthesize this rather. Okay, so a bunch of stuff is happening here. And like before, we're going to focus on the pipelining aspect, because that's what we really care about. And there's now a message here. So the thing did not fail, right? This thing synthesized. We got something out of it. But the target initiation interval that we chose, 1, was not met. Rather, the final initiation interval achieved by the tool was 3. And what you might wish in this case is that the tool actually just failed on you, but unfortunately that's not how it works. Rather, you would just, if you didn't notice this, observe that your circuit was suddenly 3 times slower. So we really want to pay attention to this. And what it says is that there's a problem with this memory in port, that it's unable to schedule a bus request, blah, 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 essentially saying there's contention on this particular interface. So we cannot do this 3 times in a single cycle. And because there are 3 axes, we can only do it every 3 cycles, which gives an initiation interval of 3. So this was the issue I mentioned, and now I want to show you how we can use sort of this imperative entry point to program our hardware to look in this way, where we can get around these kinds of issues. And in some sense, it's actually fairly intuitive the way this works, because essentially what we want to do is we want to pass values along from one iteration of the loop to the next iteration of the loop, which means it has to be persistent across loop iterations. And how do you get something that's persistent across loop iterations? Well, you pull it out of the loop. And that's essentially what we're going to do. So we have these left, center, and right values here, and rather than reading them all here, we're going to take them out of the loop and pass them along. So if we remove them from here and say outside of the loop, we now have this left value and we have the center value. Then we can now use them in here and do something clever with them. Of course, we need to initialize them to something. So if this was iteration, we have to be ready for iteration 0. So this would be the first memory location, and it would be the second memory location. And everything now should sort of look completely normal from a C++ point of view. There's nothing really crazy going on here. Now we can use the value in here. And then the only thing missing is that in order to keep having a correct value present in these 2 registers, we need to update them at every cycle. So now we finished executing I = 1. And then for the following cycle, the left will be the previous center and the center will be the previous right. So we're essentially just going to update these 2 variables. We're going to say that the left is the previous center and the center was the previous right. So we now move these other axes out of the loop, so there's only one access to this interface inside of the loop. And then we propagated the values along so that we sort of pass the values from previous loop iterations along to the next loop iteration so they can use them without having to re-access memory. And if you're thinking, why the hell doesn't the tool do this automatically? Keep this in mind that it is sort of our biggest curse and our biggest privilege is that it does not do this for us, which means there's no sneaky cache you have to figure out how it behaves. There's no weird false sharing. There's nothing like this. But we have to actually do it. The cool thing is we now have a guaranteed perfect access pattern because we explicitly only accessing memory once every cycle, and we know that this is exactly what's going to come out on the other side. So now we're going to try to build this again and see what happens. Good time for a drink of water. So take a look here. This time it worked. So we got our initiation interval of 1 that we wanted. And also, in case you noticed before, we actually got all the 3 units back. We got both the adders and the multiplier again. So this thing was now pipelined. And we didn't look at the report before because essentially it's the same thing as I showed you in the first example, but we're now back to having just this number of actual iterations of the loop plus this constant latency. Okay, so that is sort of how we can instantiate fast memory on the device essentially just by making memory that is persistent across loop iterations. So if we have this pipeline, now we want to pass values along the pipeline, or rather cache stuff so we can use it later, but explicitly. We do that by pulling out something out of the loop so it's persistent across loop iterations, and then we can sort of pass it along. And this very simple pattern is actually the primary component of most of the optimizations that can make FPGA codes fast. So if you think this is fairly simple, you're actually already a long way towards doing FPGA optimizations. So let me jump back to the slides, and please post any questions you might have. I'll try to keep an eye on it. I will share screen again. Okay. So let's talk a little bit about storage. We have a bunch of this fast memory available to us on the FPGA. I mentioned that earlier, and there are 2 classes of this storage that are the significant ones to distinguish between because of the way that you target them and because of the way you can utilize them in practice. One is a register, so the very first one we talked about, and a register in this case is basically just a collection of flip-flops on your device that can store some amount of data, 4 bytes in this case, which corresponds to 32 bits times 1. And I'll explain in a second why I wrote in this funny way. Then we have these other units that I mentioned. We have these on-chip RAM units, and they have a much larger capacity. For example, 4096 bytes. This is an example configuration of how a Xilinx BRAM unit can be configured. They can essentially be configured in a bunch of different ways depending on what you need. It's not something you do manually. The tool does it for you. But it's a very good idea to understand the granularity of these, because when you're trying to really scale up your design and you want to target these in an optimal way, it matters that you know what your chunk size is. But for now, the important point is that these have a lot more capacity internally. But again, we're going to write them in this funny way that we're going to say 32 bits times 1024 instances of these. And the reason why I'm writing in this funny way is that when we're discussing FPGA fast memory, it's useful to think about it in terms of depth and width. So these are also terms you're going to see thrown around a bunch, but they relate very much to how we think about pipelines and how we think about the performance of pipelines. And the way we think about performance of pipelines basically translates into the way we think about the fast memory that we use in our pipelines. So if we look at the register here, the depth means how many concurrent elements we can store inside the storage unit. So at any given time, if we take a snapshot of this unit of storage, we're going to have exactly one operand stored in here. Now we can write it either in operands or in bytes or whatever, but I think it's easier to think about it as operands, because that now translates directly to the number of cycles, which means that on a cycle by cycle basis, there will always be one element stored in this register. Okay, so why do we talk about it in this funny way? If we look at the right-hand side, internally inside this RAM units, we can store a bunch of these operands. You can see I drew a little 32-bit thing inside. But the way we access these is now limited. The register, we can read and write it every single flip-flop, every bit, we can read and write every cycle, but not the RAM. And this is probably not surprising. Of course, you also know that you cannot access every piece of memory in your DRAM at the same time. If you could, then HPC would be a very trivial field. So the access point to our memory is limited compared to the capacity of the memory, right? So that makes a lot of sense. But this is now quite interesting in how we think about utilizing these units of storage in the FPGA context, and it's a useful way to think about it, to think about them in terms of the width and depth requirements that you have to the storage that you need. So the depth of this BRAM would now be 1024 elements, and by depth this now means that we can store memory and not lose any data for 1024 consecutive cycles. So if we are storing something inside this DRAM, we can wait 1024 cycles before we replace the first element we put in. So the depth is essentially how much can be in there at the same time. So we have this width and the depth. So if we now go back to the stencil program and try to give this a little context, we can put these width and depth parameters on top of the little code that we just wrote. So the memory arrangement here on the right was this 1D array that I drew. We're propagating along this one dimension, and we're accessing the left, the middle, and the right values, the little arrows I drew here. And that corresponds to a width of 2 and a depth of 1, because the fast memory we instantiated was these two registers, because we needed to store both values every cycle, but also read both values every cycle. And this corresponds to a width of 2 because the access width, so the number of elements we need to access in a single cycle, is 2. The depth, however, is only 1 because at every cycle we replace the content of these registers. So both of the registers are replaced with new content every cycle. So we don't need to have more than one element stored per register per cycle. And then the total amount of storage we need is just the product of these two. So 2 times 1, we needed 2 registers. And please excuse, I've now moved over to talk about operands instead of bytes, because if we just assume we're using whatever 32-bit floating point, that's usually what we care about, that we can read 2 floating point numbers per cycle rather than 64 bytes or whatever. But you can think about it in either way, it works the same. So what happens now if we add an extra dimension to this? Let's say we take this stencil and now we wanted to do it vertically instead of horizontally, and we're iterating over a 2-dimensional grid. And you can probably guess that this is a pretty common use case. Now think convolutions or stencils or anything like this, where there's more than one dimension of neighbors we want to access within the stencil pattern. The requirements to width and depth would then change like this. So the width does not change. If I want to access the north and the south and the center element, the number of fast memory storage elements I need to access per cycle is still 2. They happen to be the north and center instead of the left and center, but they're still only 2. However, if we are iterating from top left to bottom right, that's the assumption here, the distance between storing the element, accessing it, storing it, and needing it again is now n, if n is the width of this of the horizontal dimension, which means that the total requirements, the total capacity requirements of this is now 2 times n. So 2n capacity in some sort of memory that we need to store this, because we only need to access them. We only need to access 2 memory locations, but we need to keep it in there for n cycles before we pull it out and replace it with something else. So the same pattern, but transposed now means that we significantly change the depth requirement because of the iteration space relative to the data points we're accessing. Okay, so if we jump back to the example I showed before, we had this thing where we read in the value, we stuck it in a register, fed it to the kernel, stuck it into another register, and fed it to the kernel again. Then now we're basically just going to take these and replace them with on-chip RAM units. So I'm going to show you how to do this in code, but just from the performance model point of view, or rather the storage model in this case, we did not change this W, we did not change the width of stuff we needed to access, but we did change the depth. So let me show you how that works. And again, we're now going to move a little closer to the kind of pattern you will see all the time in FPGA programming with this kind of buffering. I'll share the other screen again. All right. So we're going to jump into example 2. Again, just copied the concept into some code here. The example looks very similar to before, but now we've added an extra loop. So we have the outer loop over rows. We're going to have n rows, and the inner loop over columns. We're going to have m columns. So now we have a two-dimensional loop, and rather than accessing the left, the center, and the right, we're now accessing the above, center, and below values. So conceptually exactly the same, and it's also, you can see it very clearly from the code here that our width requirements didn't change. We still need to access 2 different points of memory every cycle. The problem now is that the distance between these has gone much larger. If you're familiar with this kind of terminology, you can also think of this as the reuse distance if you're talking about caching. And the concept is very similar here. But the basic principle is the same. Now, I'm not going to start recompiling this now. You can probably believe me that you would get the same problem as before, that this would not pipeline to initiation interval of 1 because we have these 3 accesses to the same interface. So just like before, we now need to pull these out of the loop. The thing is, now we cannot just pull out a single value because we now need to actually wait for a whole column worth of iterations before we need to access this again. So we need to actually make not just a single value, but a whole line of values. So we have our 2 buffers here. Each will now be an array of m. And accessing these, of course, means we need to access a particular index. I guess I didn't need to remove these. So now we're going to access these at the appropriate index. So this now corresponds to accessing the the 2 values directly above if we buffer them at the right time. And like before, we now need to also propagate the values. So the previous center value will become the next above value once we iterate down to the next row. So above buffer at j will become the center thing, and the center buffer at j will become the below thing. And that looks very much like what we did before. The only difference is now we're indexing into an array when we're loading it, and we're indexing into an array when we're storing it. And that is also pretty much it. But there's one little extra consideration here. One is, of course, we're using now a lot more fast memory. So the depth requirement went up, so we went from having just a single register to having m of these. But there's another issue here, which is initialization. So before I didn't really discuss it much because it was sort of simple. We just said equal whatever. But now you can see that this is not that easy to initialize. We actually need to have a whole loop to initialize this. And this has some interesting consequences, which we'll talk about in the following. But basically, we're going to need to make a new loop. And in this loop, we're going to populate first the above buffer. And then we could put the center buffer here, but then we would be back to exactly the same problem as before. We would be back to not being able to read twice from the same interface in a single cycle. So this would again fail pipelining. But this does not work. We actually have to have even another loop here. We need to have separate buffer loop. Not to say we could not do it in the other way, but if we actually want to pipeline this, which we do, we actually have to split this again, where we read this from m plus I instead. And each of these now get their own pragma and turn into their own pipelines. And this is a quite important consequence, which we'll return to in a second, that now we have not just one pipeline, but actually 3 sequentially executed pipelines after each other. But anyway, that's what we needed to do. So now we have initialized our buffers, and then for the rest of this two-dimensional thing, we can just happily go along and read out of the buffers and write back into the buffers. So let's now actually try to synthesize this. All right. So let's take a look at that. So now we did succeed. Whoops. So we see that all 3 loops were pipelined with an initiation interval of 1. You can also see different depth requirements here. But anyway, we had 3 loops and they were all pipelined. But this is now a little bit interesting with regards to the performance model, because now we're not talking about just one loop with these 2 parameters. We actually talk about 3 loops, each with their own initiation interval and their own latency parameter. And this has some implications for performance, which we'll talk about in a second. But the good thing is this works, this pipelined, and that's essentially what we needed to do. If you look at the report, we will see that this now shows up at 3 loops, but the full execution of this is still within the same realm as before, 1024 plus some constant. The constant got a bit bigger now, and primarily the reason why it got bigger is because we have these 3 loops, we have 3 latencies now. We have the latency of the first loop, the latency of the second loop, the latency of the third loop. But it sort of roughly adds up to the number of cycles we would expect, so we're still sort of doing okay. The other interesting thing to notice here is that the tool actually did choose to implement this thing using block ramps. We didn't say it should, we didn't have to. At least for Xilinx, I think for Intel also you can give hints or even commands about how these things should be implemented, but most of the time there's a reason why they're chosen in a certain using a certain unit, and in this situation here it was chosen that this should be implemented with a block RAM, which is basically these large RAM units. All right, so now we just went 2-dimensional essentially. And if you now take what I did now and you merge it with the 1-dimensional example I showed you before, plus take care of some annoying boundary conditions, you basically implemented a stencil. And there are actually, at least for a few years ago, doing that, combining what I just showed you with the previous example, and taking that, scaling it up, was already an FPGA paper. So sort of this is this fairly simple thing is starting to get into the techniques that are commonly used when you're writing FPGA code. And FPGAs happen to be fairly good as stencils, which is also why I'm showing you these examples, because we care slightly more about the stuff where it can actually do something interesting. All right. So let me pop back to the slides. Let me just see the time now. I think we might be approaching break time. So now you've been listening to me talk for more than an hour. Yeah, so I think this will be a good time to take the break. After that, I'll continue progressing with this and adding more parallelism to it and so on. But if we can get the 30-minute break now, that would be good. And in the meantime, I will also check into the discussion tab and the questions tab, answer any questions you might have there. And then we'll return after the break. Okay, we're back. I hope everyone managed to get themselves a coffee or whatever you need to stay awake. We're gonna carry on where we left off. So because of the technical issues, we were slightly behind the original schedule, so we extended the break a little bit. So you had a chance to rest for a moment. But we should still be fine to finish everything we need to finish. So let's keep going. Okay, So we left off with this two-dimensional stencil example where we took the fast memory that we had instantiated and we moved it to this larger RAM capacity block so we could buffer more values at the same time. And like I mentioned, this is already a large portion of the optimizations necessary to do stencil codes and FPGAs, which is a very typical use case for FPGAs. So to talk about width and depth a little bit, in terms of the mapping from the C++ code to the hardware, we can think about it as this two-dimensional thing, width going in one dimension, depth going in the other. So when we're talking about a low width and a low depth, we're talking about a single register. So this was the second example we showed where we pulled one value out of our loop and we essentially instantiate a register by having this persistent across loop iterations. Then the example I showed you just now was where we had still a low width requirement, but we had a high depth requirement. And what we do in this case is we need to get these RAM units, which we instantiate using either an array or streams with a certain depth. And I will return to streams in a bit. Then we have the example up here, which would be higher width requirements, but no high depth requirement. So you can think about this as vectorization, SIMD style, where we want to perform the same operation on multiple vectors, and typically we want this kind of storage. And then finally, both at the same time, where we have high width requirements, so we need to access a lot of elements, we also need to store them for a long time. Well, then there's nothing left to do but basically stack a bunch of these high capacity units and access them all. So different ways that could be, for example, an array of vectors or a stream of vectors. Okay, so one of the consequences of the way we changed the code now to have these two dimensions was that we had to have two extra loops required to initialize the circuit. And this has some consequences for our performance model, which I just want to cover now because it will get important once we have once we start having more nested loops and we have more work to do. So essentially what's going on here is we had these three sequentially executed pipelines. We had the initialization for the above buffer, we had the initialization for the center buffer, and we have the actual two-dimensional compute loop that did the bulk of the iterations. And each of these has their own runtime parameters. So the first one has a runtime of n plus some latency for that one. The next one has again n plus its own latency, and then we had the two-dimensional loop, which is the product of the two dimensions plus some other constant latency. In practice, what this means is that these are sequential. So we will end up with three different stages, each of them having this nice parallel pipeline that has these nice properties that we talked about, but between them they are sequential. So we essentially end up with a sequential execution of these parallel stages. And this can become important in certain situations, which we're going to look at a little bit. So if we look at this in terms of the performance model, if we have one stage here with some latency, some initiation interval, and some number of iterations, where then this latency is sort of the penalty we pay for draining the pipeline after we finished pushing in all the elements. Or you can also think about it as the penalty for pushing the first element to the end. It's symmetric either way. And then the next one has its own parameters. But what happens now if we put this in a loop? So let's say we have these two sequential stages. They can be sequential for the reason we just showed. For example, they're both accessing the same interface, meaning we cannot execute at the same time, but we do need to do it multiple times. For example, in our stencil code, we might have to do this iteratively. Then we would need another loop around this. The runtime would then be something like this. So we have the sums of the two runtimes for each of the pipeline, but putting a loop around it would mean we would have a term that was multiplicative with this whole thing. So not just the number of iterations, but now also capturing the latencies in this. So that means that this latency will now be paid every one of these outer iterations rather than just this one time, which was this nice property that I talked about in the beginning. So essentially there are situations where we might actually have to care a little bit about this latency, even if we do have an high n, and that is when we have multiple nested loops, and the loops it would depend on which ones of the loops are the big ones and which ones of them are smaller. So I'll go back to the example that we just looked at for the two-dimensional stencil and try to play a little bit with what happens if you add this extra time parameter around it and run it in a loop. So let me switch to the other screen. So I'll jump into example 3 here. Now you'll see something very similar to what we just coded up. It's basically the same. So we had this code, we had the two-dimensional loop, and we needed to buffer some values across different rows. So we needed to create these buffers of size m, which was the number of columns in our two-dimensional domain, so we could sort of delay them until the next row. And now what we want to look at is what happens if we put an extra loop around this. So let's say I want to also do some t for time loop here. Take this whole thing and stick that into a loop of its own. So now we have these 3 sequential pipelines executed one at a time, no parallelism between them, but we want to do that whole thing multiple times. And I want to show you what happens with the performance when we do this. But for that, we're just going to look at these constants. So we had this capital T, capital M, and capital N. So I'll open up this header file that's included with the defined. So as an example now, I've set them all to be 10. So the total number of iterations of our loop would now be 10 time steps plus 10 iterations times 10 iterations plus 10 iterations plus 80 times 10, 8 times 10. So here you would have 80 iterations plus 10 iterations plus 10 iterations times the 10 outer dimensions. So a total of 1,000 effective cycles of doing something useful, right? So in the ideal case, this whole thing should execute in 1,000 cycles, which is the time it takes to execute all of these loops without any latency penalties. Let's try to synthesize that. Okay. And we're going to open up the report and take a look at this. So what we see now is this is actually a bit nastier than we would like. So in the ideal situation, this whole thing should take 1,000 cycles, but it actually comes out as 1,500. And if we look at the report here and how the pipelines are generated, we can understand what's going on, because each of these loops carries a latency, but because these pipelines themselves are executed in a loop, these latencies are paid at every iteration of the outer loop. So because we put 10 time steps, so 10 times repeating not just the input to the pipeline, but the whole pipeline, including the latency, we're basically multiplying this latency penalty by 10 and adding that on top of the rest, and the same for the 2 other pipelines. So rather than having 1,000, we're now quite a lot above. We're looking at 1,500 cycles. And this is kind of a silly example because, of course, you're not doing a domain of size 10 or for 10 time steps, but it might actually be relevant if you're now thinking of something like having to do a convolution where you're applying a certain little domain to something else, and your innermost loops would be the size of the little window you're applying. So that might be fairly small. And then you're taking that and you're applying that whole window multiple times. And if you happen to implement this in a way where you need this initialization stage before you can start computing, that could start adding up to be costly as you're progressing along the loop. So if your innermost loops are small and the outermost loops are large, you can start paying this penalty. So I'll show you a couple of examples. So for example, what would happen if we had a lot more time steps? So now we increase the number of time steps to be 100. So this is the situation where the inner loops, so the domain where we're applying this to, the spatial domain, is quite small, but the iterative dimension, so the number of times we need to reinitialize all these pipelines and rerun them, is large relative to the domain. Then essentially we now just have exactly 10 times the number I showed you before, so still 50% worse than we should be doing. The number of useful cycles executed here should be 10,000, but we're spending 15,000 cycles doing it. So this penalty is sort of we now pay this penalty every cycle of the outer loop because the internal pipelines are sequential. So let's look at the opposite case. So now let's say we have a 100 by 100 internal loop, but we're only executing this for 10 time steps. So the ideal number of cycles for this would now be 100 times 100 times 10, so 100,000 cycles. We'll see what comes out of this thing. Here we get 100,431 cycles. So basically 100,000. And this makes sense because now we're spending the bulk of our time in the actual useful loop and a relatively smaller amount of time in the initialization loops, because the compute loop scales as this n squared, and we made the dimensions bigger, but we didn't make the time steps bigger, and relatively the number of useful dimensions increased relative to the number of non-useful iterations. So the same piece of code can be either very efficient if the inner dimensions are large, or very inefficient if the inner dimensions are small and the outer are big. So this is an important thing to keep in mind, that essentially what will give you the performance is the pipeline section. And as soon as you have a sequential component, it's very important that the sequential component is small compared to the parallel component, so small compared to the pipeline section. And this is particularly relevant, like I mentioned, with codes where you have a lot of nested loops, that you need to make sure that the innermost loops have a large number of iterations relative, well, not relative, but have a large number of iterations so they don't drown in some sort of latency. So I'm going to hop back to the slides. Okay, so there are some ways to solve this. I'm not going to go into great detail with it right now. The important thing was to understand how this affects the performance model that we had. But essentially what we could do is, if we could shove this into a single pipeline, we have these two pipelines, we could shove that into a single pipeline and remove this outer iterative dimension, then we could collapse this so the M would get absorbed into the number of iterations rather than being multiplicative with the whole pipeline. And then we would return to sort of the original scenario that we liked, where the latency stops mattering because our number of dimensions will be large. So if you think about this in terms of the control flow, we're essentially taking the control flow of this sequentiality, sequential behavior, and absorbing it into the pipeline itself. And like I said, I'll show you in a bit one example of how this can happen in practice, but it's sort of a common technique, which is not necessarily very intuitive from a software point of view, because the number of iterations doesn't change and the actual work being performed does not change, but just by how big the different loops are relative to each other, it can have a quite significant impact on performance due to these pipeline drains. But now let's move a bit ahead and start getting to the examples where we can start scaling things up. So I keep talking about these little individual pipelines, and we're talking about thousands of cycles with a few adds and molds, but we need to start scaling things up soon, because eventually we want to do, like I said in the beginning, and really utilize all the logic we have available to us. And for that, we will end up having to design not just one pipeline, but many pipelines, and it'll become clear why this is the case. So if we have this sequential situation here, where we have multiple pipelines we can execute, we would have to execute after each other. There's another way we can merge them. So one thing was actually sort of absorbing the control flow into the pipeline. But what we can also do is, if we detect that the output of one pipeline corresponds to the input of another pipeline, which could, for example, be consecutive time steps of a stencil, or reused elements that could be applied to another set of inputs, then we can take it and directly forward it to the next kernel, to the next pipeline, sorry. So if that is the case, then we basically take this AFI and we just send it directly over to the next pipeline so that it never has to go back out to memory. Because what we really want here is to avoid the data movement, and by taking the data movement and changing it from being to some memory location and instead sending it directly to the next unit, we basically save a load and a store, which will give us the data reuse we need to actually get somewhere performance-wise here. So if we can do this, it basically corresponds to this now becoming one, acting as if it was one pipeline performance-wise. So you would get the same n being absorbed into the multiplicative term with the initiation interval, and the latencies will just be additive. And same thing, if we could do the same with the next pipeline, then we can again forward the value directly and absorb the other n into our pipeline, and eventually we could end up with basically just one pipeline again. And there's nothing conceptually different from the individual pipelines we're working with. It's the same concept. You can take our pipelines and make them deeper, but from a design point of view, from the way we write the code, it changes what the code will look like and what the resulting hardware will look like. And luckily, we can use the same kind of performance model to describe what we get out of it in the end. So for this, we need streams. And this is also something that you will see thrown around a lot and used in any context related to FPGAs. This is something that exists outside of the FPGA world as well, but in the FPGA world, it is a very common way of communicating because of the way it goes nicely with the pipeline abstraction. So streams are also known as channels. In the Intel context, they're typically referred to as channels. FIFO is sort of the hardware way of thinking about it. You know, a FIFO from algorithms and data structures, basically just a queue that has first in, first out semantics. And in practice, the way we operate with it and the semantics that we use to instantiate and operate these streams in practice are just a queue, but a finite bounded queue. But these streams are surprisingly useful for a bunch of things. And just to look a bit at what the streams imply in terms of the different characteristics we've been using so far. Internally, our streams can have a buffer. So think a finite bounded stream because it's hardware. There's no dynamic memory allocation. If we want to create a FIFO or queue somewhere on the device, it needs to have a finite depth because we don't want to create a path going back to off-chip memory and path to object memory and back again every time we want to store something. So this needs to be finite and known at compile time, but it has a depth. This can be 1 and it can even be 0, so you can also just omit this entirely and communicate directly between some input and some output, but often this depth is useful just for creating some flexibility. And then on the data path itself, so the actual data that is traveling from some input to some output, this also has a width parameter. And if these two things seem familiar, this width and depth thing is because essentially streams are also just buffers. We just take buffers and we put streaming semantics on top of them because it's a useful way of programming FPGAs, but ultimately they're just a different way of using buffers. So we have our width and our depth parameters, and you can also see how the width and depth terminology also applies very well to the streaming concept, to the bounded, finitely sized queue on your chip. But the other very important thing, which will be one of the primary reasons why we're so interested in using these, is that when we now communicate between our input and our output, we put something into the stream and take it out again. It also implies synchronizing on the state of the input and the output. So if you imagine both the input and the output as being a singly scheduled block of code, it kind of makes sense that once your data falls through, one computation needs to go directly into the next. But what the streams allow you to do is you can break this up and say, I logically think about the schedule of one thing, and then once I compute something from that one thing, I can send it off into some stream, and then it's not my responsibility anymore. Then I can take another component, schedule that to accept elements coming in, and think about that in isolation. So even though they might be collaborating and communicating with each other, they mean that you can split the scheduling and thinking about how these two things interact into two separate components where you only have to match the communication between them rather than the full schedule between them. And this will be important for a number of reasons, and it's also it can also be helpful in programming these kinds of situations, because it means that you can abstract, you can split things into different components in an abstract sense, which can also make it easier to reason about their schedules. So what streams allow us to do is to have processing elements. So here's another key FPGA term. So processing elements essentially mean individually scheduled pipelines that communicate with each other. That's sort of how you should think about them. So each of these is now a pipeline, but they will now not be sequential, but rather all be operating individually on their own with their own schedule, but connected to each other by streams, which will synchronize their behavior with each other. So each of these dashed lines is now a stream that communicates one of these processing elements with another. When we're writing HLS, these are expressed differently depending on which tool flow you're in. In the Intel world, these are OpenCL kernels. So each of these would be a separate kernel that you would launch from your host code, and they would all be running at the same time on the device, and they can communicate. Or in Xilinx, they all live in the same sort of top level scope, but then you can create scopes where the sub functions are scheduled as different processing elements. And the end result is the same, but this is a place where the two vendors have sort of diverged a little bit in how things are represented, which can give you some portability issues when you're expressing things in processing elements. But unfortunately, that's how it is. And the properties L and I remain. So each of these processing elements still have their own latency, initiation interval characteristics, and they all continue to apply the same way as they did before. But even more interesting, we can now take this whole thing and again just think of this as another pipeline, just even bigger now. And this global pipeline is interesting, and it has a bunch of properties I'll just go over, which makes it useful, which is important to keep in mind for using these to program with. So one is what might seem trivial, but what goes in must come out. So when we have two processing elements connected to each other, whatever we write into the stream between them needs to be read. And this sort of makes sense. If you think about this as a data flow program, for example, then whatever you produce must also be consumed somewhere, otherwise you can get stuck or even have deadlocks. But this is even more the case when we're talking about hardware, because there is no way to go and pull an element out somewhere. These will be signals propagating on the chip, and if there's something that is suddenly full on your device, it is full forever. Your program is deadlocked until you essentially reconfigure the device. So it's very important that we have this, that we program these consumers and producers to where we really understand what comes out and what goes in. But it is also an advantage in the sense that we can split it into this. So we can really split it into thinking about only do we produce what we're supposed to produce and do we consume what we're supposed to consume. Okay, so the other important characteristics comes back to the whole initiation interval business, which essentially slow dominates. So if we have two of these processing elements communicating with each other and they don't have the same initiation interval, well, then you're stuck with the slowest one of them. You can imagine this. You can imagine this quite easily if you have one element that produces an element every cycle, but the following element can only accept a new element every second cycle. Well, if you look at that circuit as a whole, it's only gonna execute every 2 cycles. It doesn't matter how fast the first one produces if the second is not ready to consume. So again, might seem fairly simple, but a very important thing to keep in mind, because it means when we design these global pipelines, we need to make sure that we don't have a bottleneck somewhere. You can have 1,000 of these processing elements communicating with each other. If one of them has a higher initiation interval and it happens to be in the critical path of your circuit, your whole thing will be slowed down. So essentially, initiation interval continues being very important now, propagating beyond just a single pipeline, but to this whole network of things that we will connect. And then here, sort of the more cool news is that this whole thing still just acts as a pipeline. I mentioned this at the very beginning when we were talking about the performance of our little loop that had 2 adds and a mult is the depth is free. So whatever we stick in here, however many processing elements, whatever logic we put in there, if all of them are pipelined, if they all have this initiation interval of 1, and they all produce and consume the same amount of elements, it will have the same runtime no matter how much you put in there. And this is of course super cool, because if we can actually put something useful in there, if we can put some useful logic in between the beginning and the end that do something good for us, it will not increase our runtime. Our runtime will just be whatever it started with. And this will basically be what this is sort of the fact that we will use to build all our parallelism now for the rest of the tutorial, is that we need to add stuff to this depth to give us more useful compute in practice. So let's take a look at what this looks like in the Xilinx world. Okay, close this. Okay, so there's a bunch of stuff to unpack here. We've reached the point where I will not manually code everything up, because there will be too much typing and too much margin for me to make errors, but I'll slowly go over what's going on here. So the example should be familiar. This is now back to the first little stencil example I showed you, where we had 3 reads from an interface that we fixed by moving 2 variables out of the loop and initializing them before the main loop, and then running the main loop, updating them along the way. The important thing that's different here, as you might have noticed, is that we've replaced these array reads with push and pop operations. So if we look at the interface here, we don't get pointers in now, we get in these stream objects. And the stream objects are these queues that we've been talking about. They might have some depth, but the important thing is that they expose now these queue semantics to us. So we, instead of reading from some certain index, we just say, give me the next element out of the stream and I will do something with it. So we have these 2 pop operations that give us the 2 consecutive elements that we will use as a left and center location. Then we happily go along the loop. Every iteration, we pop in the next element, we do the computation just as usual. And now the important thing is that we can take the result and push it down along the stream. Okay, so far this does exactly the same thing as it did before. This time there'll be a bit more code. So if we scroll down a bit, there are 2 extra functions here. There's a read memory function and a write memory function, and they're very trivial. The read memory function takes in a constant float pointer, so an interface to memory or somewhere where the data comes from, and a stream object, and then it just takes all the elements out of this array and just pushes it into the stream. So essentially, we're just doing the same reads we did all along. The difference is just that we first take them, put them into a stream instead of feeding them directly to the circuit. And symmetrically for the write, do the same thing. We loop over all the entries, and we write out the elements by pulling them out of the stream and then pushing them back to memory. And there's a -d here, which I'll explain in a second. So this time I've included a bit more. So these this is now the wrapper code, which is the top level code that will actually be compiled to the kernel. This was actually present in all the other examples I showed you, but I hid it away because it wasn't really relevant at the time, because when we do these very simple things, they're basically trivial. But now they're a bit more interesting, because now we're going to do a bit more interesting things. And this is the part where Xilinx and Intel diverge a little bit. In the Intel world, this function would not exist, and rather the communication would happen outside of here. But I won't go into that right now. I'll just focus on the Xilinx way. So this is our entry point now. So the thing that will be exposed to the host side, the sort of kernel entry point that we can launch, just like you would have a GPU kernel or something, which means that we need to now define how it interfaces with the world. This is hardware. We cannot dynamically access whatever we want, so we have to say, I am accessing now some kind of port. Details are not important, but this essentially means we're reading from DRAM. So these 2 pointers will be 2 entry points into DRAM, read and a write to DRAM, and then some control signals that we need to actually run our code. And then If you scroll down here a bit, we can now see how we can start instantiating these processing elements, which is what we want to do to start scaling up the design. So there are some macros here. I'll explain what they mean in a second. So the first thing to note here is there are these, there's a bunch of streams. I actually made a whole array of streams here that are called pipe. So we have capital D +1 pipes. Then inside of our code, I have a read memory function, which accesses the first pipe, a write memory function, which accesses the last pipe, and in between I have a loop. So this loop calls our actual stencil function. And the interesting thing here now is that every iteration of this loop calls the stencil function with a distinct entry into this pipe array. So the first iteration will give it pipe 0 and pipe 1. The next will be given pipe 1 and pipe 2 and so on. And this means that in practice, each of these will now be spawned and connected to different ones of these stream objects, depending on which iteration it is. The important additional thing here, which is why this whole thing works, is this loop. So this loops means something entirely different than the other loops we've been using. So this also returns a bit to the problem of these tools trying to use standard C++ without any extra syntax, when actually this does something fundamentally different than other loops in our code, but you're gonna have to bear with me here. So this loop is now unrolled. And you might know the unroll transformation from software, where essentially all it does in software, it takes your source code or the body of your loop and it just pastes it a bunch of times before you compile it. This can be useful because it can expose some instruction level parallelism, for example. But in the FPGA world, this is much more powerful. So essentially what we're doing here is the same. We're taking this piece of source code and we're pasting it in a bunch of times. But now keep in mind what I mentioned earlier, which was that everything inside the body of our loop does not affect the total runtime of anything. And essentially what we're doing here is we're building this global pipeline. So we're taking a bunch of these and instantiating them sequentially after each other and connecting them with each other statically at compile time. This capital D is not a compile time, and this unroll is fully unrolled. So basically we're just going to have a sequence of these calls to this function that will now be scheduled in parallel rather than sequentially. The reason why they will be scheduled in parallel is because of this other pragma. So in the Xilinx world, when you want to do these processing elements, you create them all as individual functions like I showed you above, but the way you sort of actually instantiate them and connect them is by having a top level sort of master function where you call them all as if they were functions and put them in this data flow scope, which basically just means every function call inside this scope, so the scope here is the whole function, will be an individually scheduled independent processing element that are only connected using these stream objects. So effectively what we're going to get now is a read memory processing element, a write memory processing element, and capital D many of these simple 1D stencil processing elements all operating in parallel. And just to give you a quick background, the reason why this is in some function called HLSlib data flow function blah 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 is because in the infinite wisdom, the way Xilinx created the simulation flow for this, it does not match the hardware execution flow. So if you read this as a C++ function, essentially what you're doing is you're executing this function, you finish executing it, you go to the next function, you finish executing it, and so on. When actually what we're doing in hardware is we're executing all of these in parallel. And they basically didn't give a solution for this. So the way the Xilinx simulation works out of the box is that it will really execute everything at the same time, which means that these streams will have to contain the whole depth of the stuff they have to hold before the next stage is executed. This sucks, so our lab builds an abstraction on top of that, which essentially just wraps these function calls in some C++ threads, launches them, and lets them all run in parallel in simulation mode. And in non-simulation mode, they will just be inlined as normal functions and be compiled to parallel hardware. But that's just a detail of the syntax. The important thing is here, all of this will now be parallel code. Okay, so this the thing I just showed you is now surprisingly powerful. So let's take a look again at some of these constants. I'm going to open example for.h. So we have some values here. We have n equals 1000 and d equals 2. So that means the inner loop here is executed for 1000 cycles, and this loop will only inline one instance of this. So I'll start the synthesis for this. There's a question about the overhead of HLS. Let me get to that in a second. It's not a short answer, basically. Okay, so let's take a look at this report. So this will look very familiar. It's the same thing that's been happening all along. We have a pipeline with 1024 cycles. But if you think about this for a second, we're actually executing three different things here. We're executing a read memory thing, write memory thing, and the compute itself. But because all of these were scheduled as these independently scheduled processing elements, it means that this whole thing can sort of be clocked and operate in parallel. So the whole runtime of our circuit will just be essentially the maximum of these three elements plus the latency it takes throughout the pipeline. So exactly the same context we had for individual pipelines, but now applied to all three of these elements. And that's all good and well. That doesn't achieve anything else that we didn't achieve before. But now, of course, the interesting part comes when we increase this depth parameter. So now let's say we want to increase this depth to 8. So what that means is that this loop will have 8 iterations. These iterations will be fully unrolled, so we will paste in basically 8 times the source code of this, and all of these will now be processing elements of their own. So let's try to synthesize that. Right. So already here you see some interesting stuff going on. Applying data flow to function, blah, 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 to extract 10 process functions. So now what it's saying is it's actually detected all of these different elements in my source code. And all I did was I changed one constant to be 8 instead of 1. But because it was in this unrolled loop, it pasted in the function call 8 times, which means each of these now corresponds to a individual processing element that will have a real hardware equivalent. So now it did a bunch of stuff here. It instantiated all our code. And if we look at the report now, the very, very important thing to note now is that the runtime did not change significantly. Before we had 1012, now we have 1119. So the latency changed because we added more steps in the depth of our computation. But the number of iterations that we pushed through this pipeline is still just 1024, 1013 to be exact, which meant that the total runtime barely changed for this depth parameter. And if you think about this, this is very powerful because if we can figure out a way for this depth parameter to actually give us something meaningful, of course, that is now the interesting part. But if this depth parameter gives us some computations that actually do something useful that we care about, it means that we are increasing the number of the amount of parallelism and the amount of hardware instantiated on the chip that will do useful computations just by tweaking this one parameter. So this is what we're going to want to be doing. And from the stencil point of view, this could be one example. So if we're in this case, we could say we're iterative. Well, we're applying a number of blurs, right? We want to blur this thing 8 times. Well, we increase the depth to 8, and then you get a more blurred image. Not the most exciting example, but you could imagine how this could do something useful. The more interesting application in terms of stencils is that if you need to apply your stencil for a number of time steps, you can even unroll your time steps and say we're executing time step t plus 1, t plus 2, t plus 3, t plus d, while we're still doing t, and get parallelism in that way. And we'll talk about it a bit more, but I think you can start imagining that if you can structure your code in the right way, this has some very powerful consequences. Okay, so let's go back to the slides. Second, here we go. All right. So let me just answer the question in the question post first. So the question is, how close can you, with reasonable time investment, get to VHDL/Verilog in terms of resource demands? So how much overhead does HLS add compared to writing your RTL directly? And the first, this is sort of a multi-stage answer. The first stage of the answer is you should ask yourself, why do you care? I don't mean to sound rough, but it is a trap to think about resources being a constraint before they are a constraint. So think about this in terms of premature optimization. If you're talking about HPC codes and you're talking about HPC oriented FPGAs, they are typically very large. And in fact, the problem is not spending a lot of resources, it's the opposite. It is uh, figuring out how you can spend more resources. So figuring out how you can use more resources to do something useful for you. And essentially, it's only once you reach the point where you're actually out of resources on your large FPGA, then you can start thinking about how could I utilize the resources that I'm using better. But it's very important to not start worrying about resource overhead before you are actually running out of resources. And it is surprisingly difficult to use all the resources on a large FPGA. If you're working with some little embedded FPGA, then granted, then this becomes trickier and you might have to worry about it more. But you really need to make sure that this is actually your problem. So in terms of the actual overhead, it really depends on the style of code. So for purely computational circuits, so let's say you're just computing, you're just applying a bunch of mathematical functions or something, the overhead does not matter much, because what HLS does is instantiates these pipelines with a bunch of floating point units in between, whatever it needs to compute it, wires that up in a way where it can achieve a high frequency, and that is basically what you would have been doing otherwise if you were writing RTL. There are cases where using RTL means you can use certain tricks that the HLS tool might not know, but in terms of just instantiating a computational circuit, the HLS tools do that just fine. The situations for HDL might be more important is if latency is in fact critical. So if every single cycle matters for some reason, for example, you need to turn around a signal faster. So you get in a signal from your Ethernet port and you need to very quickly send a signal to your DRAM, and every cycle really matters. The HLS code is not so occupied with shaving away every cycle. The HLS tool is occupied with satisfying your throughput requirements. So this might be a situation where you could be interested in writing the RTL code to quickly turn around a signal to bring it back out on a different bus or something. If you're just doing computations, I would say you don't get much from HDL before you're really to the point where you're already using all your resources and you can do smaller tweaks to start getting the extra performance out of it. So that's sort of the long answer, which is don't worry about it before you have to worry about it. And when you start worrying about it, it has to be a situation where either you have a cool trick up your sleeve where you know you can do something clever with HDL that you couldn't do with HLS, or you have a latency critical situation. So just please post a follow-up question if you want more details on that. I cannot give you an exact percentage or something because that really depends on the situation. But generally, you're fine with HLS when it's computationally heavy. Okay, so unrolling was a tool that I used to instantiate more of these processing elements, and unrolling will basically be the name of the game for much of the remainder of this tutorial because it is our tool to create parallelism, which is interesting compared to how non-significant it is in a software context. So the loops I've been showing so far look like this. We had some loop going over some amount of iterations, and we put this pipeline pragma inside. And what that meant is we created these pipeline circuits that we drew like this. So we have some adder in this case, and we execute that over multiple cycles. We feed in multiple operands, and we keep executing it for these 4 or n cycles. Now, if we take exactly the same C++ code but we switched up the pragmas a little bit. So now we put the pipeline pragma outside the loop, and we keep the unroll inside the loop. Quick side note, this is Xilinx syntax. Intel syntax, the pipeline pragma applies to the following loop, not the scope. So then you would have to move it out even further. But for this example, it means that the pipeline pragma now applies to the outer scope, not the inner scope. And this little change fundamentally changes what you get out of it, because what you're saying now is you're pasting in the source code 4 times in a pipeline section. And again, let me remind you, everything in a pipeline section has to be executed every cycle, so it has to correspond to hardware, just like the very first example we had where we had the 2 adders. So this essentially corresponds to this piece of hardware. By moving the pipeline pragma out and having the unroll inside, we took this whole thing and we duplicated it 4 times to get the sort of vectorization style scenario. So every instruction in a pipeline section is separate hardware. So another very important thing to keep in mind, because this is really a powerful tool. So the way we create all this parallelism now is we need to essentially shove more instructions into our pipeline section so that they will be scheduled as parallel pieces of hardware that could end up doing some sort of useful computation for us. This is our tool for scaling. So if we start by having some operation, we can unroll the width. So that was the example I just showed on the previous slide. We can say, now we create 2 of these next to each other. We can also unroll in the other direction. And that was what I showed with the stencil example just before, where we didn't unroll it in sort of the SIMD sense, but we unrolled it sort of vertically by putting multiple of these elements after each other. And even better, we can also do both. So now we can expand it in one dimension and expand in the other dimension, and then boom, we get this 2-dimensional scaling. On the width side, you should think of this as SIMD style vectorization, so spatial locality, increasing bandwidth utilization to feed more to your compute in a single cycle, and essentially creating sort of GPU style SIMD, more parallel compute in this horizontal vectorization way. Whereas the other dimension is temporal locality. So we have a very clear mapping here. We have spatial locality from vectorization, and we have temporal locality from this depth unrolling. And the cool thing is that the temporal locality is explicit. If you have ever done time tiling, if you've ever tried to take a GPU code or CPU code and get performance out of time tiling, so exploiting temporal locality in a non-obvious way, this is hard, and it also gives you extremely ugly code. So although we have to do a lot of verbose things now to get this to work on the FPGA, the cool thing is if we can actually make it work, we can explicitly use our temporal locality to achieve more parallelism in a way where it's really readable from the code. You can look at your code and say, I reuse this element this many times, and I increase my parallelism by this amount, and thus I have this much more reuse. So with that, we're going to get into everybody's favorite example. If you've not seen this before, then I will be confused. We are going to take a look at a good old 3 nested loop matrix multiplication code, and then we're going to apply a few steps to see how the optimization process would look like on an FPGA, and how we can use the spatial and temporal locality terminology, the spatial and use the spatial and temporal locality in the code to do these 2 kinds of unrolling. And we're gonna solve some extra problems here that will occur that will be common to ageless optimization in practice. So the first thing to note is this loop order and how the accumulation works, because this will touch on another very important concept that I mentioned very early on but didn't get back to yet. So if you remember, I had this slide about initiation interval and why do we care about high initiation interval, because we should just set it to 1. And this is another classic case of why initiation interval is not just 1 when you want it to, but you have to actually deal with some issues. Because what we're doing here is we're reading into a memory location. we're writing to C at index n comma m, and n comma m is not an iterator of the innermost loop. The innermost loop iterator is not part of that index, which means that every cycle of this k loop, I'm saying cycle, but every iteration of this k loop, which would then in a pipeline scenario be cycles, we will be trying to write to the same memory location. And this is now a problem, because to do that, we have a data dependency on that memory location. In order to do this, we have to read the value in this location, add the product of the A and B contributions, store that back to the C before we can read that result and apply the next product of A and B coming in. So every iteration of this loop will depend on the previous iteration of this loop. So essentially what we get out of this is an initiation interval of maybe 8 or whatever the tool would manage to magically schedule this to, but basically not 1, because there's no way you can schedule this without waiting for the result of the previous addition before continuing the next. And this I'll show you in practice, and we'll actually try to solve that in the code, because this is something that if you decide to develop HLS codes, you will definitely see this. Like I said, in particular with Xilinx, but also with Intel codes, whenever you're using a non-trivial accumulator or another data type than 32-bit floating point. So it's a very, very common scenario that pops up all the time. Okay. So let's jump over to example 5. I am losing my voice a little bit here. So here is your run-of-the-mill triple nested loop matrix multiplication code written with a little extra pipeline pragma. The only thing different from what I showed you in the slides is that I explicitly took this accumulation variable and I wrote it out. This is actually not strictly necessary. Even the HLS tools can actually figure out how to do this, at least in some scenarios. But we need to be very explicit here that we're taking an accumulation variable and then we're updating it every cycle, and then we need to write it out in the end. This is not gem, right? We could also read in the value of C here, but whatever. For the sake of this, we'll just do it as a regular matrix multiplication. So here it's very clear that we have this single register, and every cycle we're accessing the same single register and trying to write to it. And this creates this issue with the loop carry dependency, that every iteration of this loop will depend on the previous iteration of the loop. The multiplication is not an issue. So multiplying this element from A with this element of B does not depend on the value of this accumulator. So that does not contribute to the problem. The problem comes with this add. So this add requires the previous value in order to start computing the next value. So the problem will arise only from this add, just to be clear. So if we take a look at this pipeline section here, whoops, we can see that now it's really crying a lot. So we had this loop that we tried to schedule to initiation interval of 1, and it did not manage. It got initiation interval of 3. In fact, 3 is quite impressive here, because this operation takes 8 cycles. So somehow some tricks were involved here. But at the end of the day, we would now already have a 3x multiplication penalty. All right, so what does it say? It says that there's a carry dependence constraint between f add on this variable ACC or accumulator and essentially itself. So it's just saying that this line of the loop depends on this line of the loop, which makes sense. That's what's going on. And because of that, it cannot schedule this in a single cycle. Even worse, we also managed to now get a horrible critical path in the circuit, which might affect the clock frequency. Disaster. So we need to deal with this. And there's sort of a few stages to this. I'm just going to do it in the simple way and briefly mention to you sort of how we can adjust it. But the sort of first easy thing we can do is we can basically just transpose this loop. We can reorder our loops so that we don't have this dependency. And whenever you're trying to solve a problem like this, where you have a loop carry dependency, the solution is always some sort of reordering of loops. There are a bunch of different scenarios. They're all in the paper that I mentioned. We go through them one by one, but they're all slight variations of the same concept. We need to find multiple loops. We need to reorder them in a clever way so we don't have this dependency. I also just want to point out this is not fundamentally different from optimizing reduction codes on a CPU. CPUs have exactly the same problem. You just don't see it very clearly. If you run this exact code on a CPU and you don't have a very clever compiler, or rather you didn't give it permission to reorder floating point operations, you will have the same problem. A ALU in some Intel CPU or whatever also has an initiation interval for ads, or latency for ads, sorry. So you would have the same dependency, which would give you this throughput penalty. You just wouldn't see it because there's no tool telling you that it couldn't meet the throughput requirement. But the solution is the same. So the way we're going to solve it this time around is just going to reorder the loops. So I'll take the K loop. So the K loop is the reduction dimension, just to be clear, the one that's collapsed and disappears in the C matrix, and we're going to move it out. So we're going to do that. So now this accumulation variable cannot be just a single value anymore. We are now accumulating into different partial outputs. That's sort of the whole point, because if we had to do it into a single register, we would have this issue. So we need to take our accumulation variable and we need to move it out. But now this accumulation variable needs to really hold all these partial values, so we cannot have it as a single value anymore. We need to have it as all the columns of the output. So we're going to make it a size capital M, which is a number of columns in the output, and B, entries wide. Then here, we're going to need to index it into the right place. And when we write it out again, we also need to move the write out. We need to put it out here. And this now needs to go into a loop of its own. And now, if you keep in mind what I've been talking about in some of the earlier examples, this now means we again have two sequential pipelines. So this is something we now potentially need to worry about in terms of this pipeline not having to be too big compared to the other pipeline. So it wasn't just examples I made up. This is really already now we're seeing that these sort of problems can occur. So now we have two pipelines instead of one. But in principle, this sort of fixes the issue. The remaining thing we need to do is initialize this accumulator. And we can put a loop here. But actually, I'm not going to do that right now because, as I promised earlier, I want to show you another quick little trick, which is very useful in practice, and then you can use in a lot of scenarios to avoid these initialization loops, which is basically implicitly initializing stuff inside here. And it's basically the inverse of what you can imagine is a good idea in a software situation. Typically in software, you want to avoid branch mispredictions. So you would want to have a single loop doing one operation, then another loop doing another operation without an if, because you might have branch misses. Except if you're aiming for cached locality, blah, blah, blah. But the interesting thing about the FPGA circuits here is that conditions are essentially free. So we can predicate stuff as crazily as we want, because at the end of the day, the FPGA can clock all the logic we instantiate at the same time and just only use the output that actually satisfies the condition in the end. So predication is sort of built in everywhere in the code we write without us having to do any extra clever tricks. So putting more control flow into our loops is actually fairly cheap. Of course, it costs a little bit in the overhead logic, but it's really fairly cheap compared to the issues you would have with branch mispredictions in the software context. So all that talking, essentially what I wanted to say was that we can do a little trick here to avoid this initialization, which is doing the following. So we can say the previous value is now predicated on where we are in the iteration space. So if we're on k equals 1, so we're just beginning our collapsing a new dimension, we can say if k is equal to 0, then we reset this accumulation variable. So in this case, it will be 0. Sometimes you have to be a little explicit about it. I'm just going to do this just in case. gonna make sure it's a float 0, or otherwise we have to actually go back and write this, read this accumulation variable. And then in here, instead of a plus equals, I'm gonna do previous plus that. I could of course also put this whole ternary operator in here, but I think this is a bit more explicit of what's actually going on. So what we did here was we basically just avoided having an extra sequential pipeline out here by having this implicit reset in here. And we could potentially do something similar with the write out. But let's not make the code too complicated for now. I just want to show you that little trick because it's quite useful. So I'm going to run the synthesis again and throw some water into this desert. I hope I didn't freeze. So this time around, let's see what's going on here. So, well, keep doing that. So actually what we see here is disaster. So what's going on here, we still didn't manage to pipeline this loop. And this is one of the situations where I could sort of be clever and hide this away, but at the end of the day, I think it's actually more useful if I show you this. This is basically just a situation of the tool not being particularly good at inferring the dependencies correctly. So if we look at this loop and we read this whole thing, we can see that because we're iterating over m in the innermost loop, we first read from this index and we write to that index after we read it, and we cannot write to this index before we've read it because we are reading it at index m and writing it at index m. This is a safe operation. But in this instance, the tool did not manage to detect this. And the interesting thing is in the next version of the tool that I also tested this with, this actually works. So this is just, you know, getting lucky with how good the analysis of the tool happens to be that you're using at the time. But in this case, it didn't manage to infer that there's actually no dependency here. So here we have to be a little nasty and actually say it explicitly. So this is getting into the sort of more nasty territory of this programming, because we really would prefer not to do this, but I'm just going to show you because, like I said, I'm not advertising any vendor tools here. So what we have to say is that there is no dependency here. I mean, the syntax is not important, but essentially we're saying the dependency here is false on this variable accumulate. All right. So then we can run this thing again and see if that is any better. In order to do this analysis, of course, the tool would also have to know all these constants. So in this case, it actually does capital M, capital K, capital N are all known at compile time. But you could also imagine scenarios where they're not. So if this was parameter passed from outside, it might be more reasonable for the tool to not know this. So then it could be that capital M was really small, so it would have to go back and read it very soon after and reset it again, and then it would be more reasonable that it didn't manage to do this. So let's see, so this time around, we managed, I think. Yeah, exactly. So this time we managed. It got the initiation interval of 1 again. A lot of loud complaining here that there was explicit, that we explicitly disallowed this. But essentially we had to, in this case, to make it work. And just to be clear, definitely don't do this unless you have to. Like I said, I just wanted to show you that this happens in real life, but preferably your tool knows how to do this and you don't have to worry about it. But there's situations where you unfortunately have to actually believe that you're smarter than the tool. And as you know, this is very dangerous because most of the time the tool is smarter than you, but not necessarily. Okay, so we managed to do that by shoehorning in this little extra pragma here. And one other little thing I wanted to do here, which is not necessary, but it's just nice to show this explicitly, is that if you notice the indices into this A array here, it does not depend on the innermost iteration variable. So there's no lowercase m in here. So if you want to be explicit about it, we can move this out and say we're actually reading, I'll just copy it from here. we're actually only reading this once, and then we can use it inside the loop. And it's nice to make this explicit just to show you that this is a nice consequence of this reordering, which we're actually going to be using a great deal shortly. So this is important. So in the innermost loop, we're actually only reading one place in memory, and that's kind of cool. So now we're only reading from this B matrix, and we can reuse this A element all these M times, and suddenly we got a lot of temporal locality. And just keep that in mind, because like we said before, temporal locality is one of our sources of parallelism that we need to utilize shortly. Okay, so just briefly before we go on, let's just take a quick look at the reports here. If we look at example 5.h, it's currently a 32 cubed iteration space for matrix multiplication, and 32 squared is 1024. So 1024 times 32 is approximately 32,000 something. So you can see we got pretty close here with 34,000. So this does now work nicely. We have a fully pipelined circuit, and the number of cycles it takes to execute this matrix multiplication is now really just the number of useful cycles plus some relatively small overhead. So that is one step along the way. So now we created a matrix multiplier that does one floating point multiply accumulate per cycle. This will be absolutely abysmal performance in practice on a 200 megahertz device. So this is definitely not enough, but it's an important step along the way. So let us keep going. Okay. So where do we go next? What we did here was we took our iteration space, we transposed the input iteration space so that we didn't have this loop care dependencies on the accumulation variable. So we got a code that looked something like this. We should definitely note here that this came at the cost of buffer space. In fact, I made this buffer that was capital M large. And you can imagine that if you're actually doing any sort of real matrix multiplication where you're not lucky and have some very little skinny matrix, capital M can be extremely large, and also it can be an unknown variable. And of course, this is not necessary in practice. It only needs to be bigger than this latency in order to solve the problem we just discussed. It was just a bit simpler to show you just now, and basically what you would need to do on top of that is tile it. The good news is it's no different from how you would tile in any other context. It just needs the extra nested loop. But now let's look at locality. Now we want to get some parallelism out of this. Finally, let's see. We are 3 hours into the beginning of the tutorial, and now we start to talk about the parallelism. All right, so now we really want to get some parallelism out of this guy. And the important thing is now to look for the opportunities for parallelism in this program. So there are two places we can see this. One is the good old spatial locality. This innermost loop is vectorizable. As you can see, that we're just accessing this B, capital B, completely sequentially, so we could make our bus wider and read vectors instead and get spatial locality. But the much more interesting one is this guy. So the reason why I hoisted it out before was because this is now very important. We are reusing this A M times in the innermost loop. So how about just doing more of that? What we can do here essentially is saying, instead of reading one value of A, let's read some amount of values of A and then reuse all of those in the innermost loop. So we spot an opportunity for temporal locality, and then we need to go and actually exploit that in practice. So I showed you this thing before, the two dimensions that we can unroll, where one here we can unroll. This is supposed to say capital M. I thought I updated this. So one is the spatial locality part, where we can unroll in the M dimension, and the other is essentially tiling these rows, so the number of values that we buffer and read at the same time. The vectorization part spends bandwidth. So there's a limit to how much we can do this. At some point, we're going to run out of bandwidth. And if you have one of most contemporary, very measly FPGAs, you will have some pathetic 77 gigabytes per second, whatever. So factor of 10 less than your P100. So this is not your greatest opportunity for performance. But this guy over here only needs buffer space. So if we're a little clever about our tiling and we know what we're doing, then we can basically just scale up our performance by adding more temporal reuse, spinning more buffer space and doing a reuse. So let's take a look at that. And this is going to be the part where the compilation times are starting to be fun for a live demo, but we will manage. Okay, so the code expanded a little bit. It should still look fairly familiar, but some things happened. We still have our loop order from the previous version I showed you, but a few more things have snuck in now. You remember before this accumulation variable became capital M? Well, now it's capital M times capital D. Okay, so capital D is back, our good old depth parameter, which is our tool for increasing temporal parallelism. Then the main loop in here, our column loop, we now put an extra loop inside, because what we can do now is when we read in this value of B, we apply it not just to one buffered value of A, but to multiple values of A, specifically to capital D values of A. So for each of these, we do the same operation we did before. We do a little clever initialization trick here, and then we read using the index into this array, and we do the operation before using the index into array. And this inner loop is unrolled. So remember that this means that this is basically just the source code will be pasted in and just be parallel inside of this pipeline section. So we're increasing the number of useful instructions or lines of code that will do useful computation in the pipeline section, which means we get more parallelism without increasing the runtime. But it's better than that, because we want to not just not get more runtime, we want to reduce the runtime. But we can do that now, because now what we did is we treated multiple rows of A at the same time. You can see here is the buffering loop. We increase the A buffer to have multiple entries, and then we read in multiple values from A before we start streaming the values of B in. And that means, because we're actually treating multiple rows at the same time here, that we can cut the outermost loop by a factor of capital D. So now we're not only increasing the amount of work done, we're also decreasing the total number of cycles we need to execute a program, essentially by folding the iteration space. So you can think of it as you take our iteration space, increase parallelism, and when we map it to that, we can fold the whole iteration space by that amount of parallelism to decrease the total runtime. But really very explicitly here, right? We're really explicitly saying we have a factor of capital D, less iterations to go through. All right. So the write back of C again now becomes a bit more complicated, double nested loop, but that's essentially the idea. And like I promised, we can do it in both directions. I split this into two because I go over them one by one normally, but we are a little behind schedule, so I'm gonna show this directly. So now I added the other dimension as well. So we had this unroll thing and the outermost thing, but we can also do good old vectorization where we just cut the innermost loop and vectorize by a certain factor. And the way this is done here is we just replace the data type. So the data type of B became a vector of T. The data type of C became a vector. This is defined inside of example 6 at H. It's basically just this this vector type. So this is not important, but it corresponds to a vector. And now we have cut the outermost number of rows by capital D, and we have cut the innermost loop over columns by this vectorization factor, so capital W. So we're now doing two dimensions of folding. We're doing the depth folding in the rows, and we're doing the width folding in the columns. And both of these are reflected in essentially unrolled loops. One unrolled loop being the one over depth, and the other is sort of tucked away here. You don't see it explicitly, but that is in this operation here. So we actually, every one of these adds and molds is now a vector add and a vector mold. So you can imagine that as inside of this, we actually have an extra unroll. And in fact, if you write it in completely plain HLS, you might have an extra unroll here, but I think it's a bit nicer to use vector types. But looking at the iteration space one more time, if you looked at this from a purely C++ point of view, the number of iterations have not really changed except for the vector type here. We're still doing n divided by d, but then multiplied by d in here. So the iterations didn't change from a C++ point of view. But from an FPGA point of view, it's very different because this loop is unrolled. So we took some of the pipeline loops and we made them unrolled loops instead. So we moved them from being sequentially executed in a pipeline to being executed in parallel in an unrolled loop. And by doing that, we cut the total number of cycles by doing this folding trick out here. Okay, so in some sense, that's basically what we need for matrix multiplication. Now we can just crank up these parameters and get all our juicy parallelism. So let's try to build this. So I'm going to build this code, and while we do that, let's just take a quick look at example 6.h. So in here, I've set the depth parameter to 4 and the width parameter to 4. So that means, looking at the code again, we have cut the number of rows by 4, and we have cut the number of columns by 4. So if we think about the total number of iterations it should take to execute this thing, we are working with 1024 cubed iteration space. Then our purely pipeline version should be 1024 cubed, which is about a billion iterations. But now we cut that by 4 by unrolling the rows, and we cut it by 4 by unrolling the columns. So what we want to get out of this is basically this divided by 4 for one unroll and 4 for the other unroll, which is now approximately 67 million cycles. So let's take a look what comes out of this. So you can see here that we are getting there. So we have here 73, 74 million cycles. So we definitely cut this very far from being 1 billion, but not quite to the point we would like. And this now comes back to all the things I was talking about earlier. The nested loops here are fairly large, but because we are now folding these dimensions, we're actually reducing the number of useful iterations relative to the non-useful ones. If you take a look at the code over here, the more we increase this depth thing, the more we increase the unrolling, the more we're executing this loop, which does no computations, and the less we're executing this loop that actually does computations. And of course, it's still beneficial because the total number of iteration goes down, but it does not go down as fast as we would like it to. And I think the best way to show this is if we crank this up to something quite high. So let's say we have a width of 16 and a depth of 18. So now we're really going nuts with the parallelism here. Then we have to see what comes out of that. So
Johannes, if I may interrupt you.
Of course.
So AV asks for a confirmation that we want to move to QA in 2 minutes.
There is no distinction between this and QA because it's only me anyway. So essentially, nothing has to change from the AV point of view. I'm gonna finish these examples and then just transition directly into the Q&A part. Okay, so what we would like now is that this thing cubed would be, the total number of cycles would be this thing cubed divided by 8 times 16, which would be now 8.4 million cycles. Let's see what comes out of this. Well, now we're up to 12 million cycles. So now it's even 50% worse than the ideal case. And this is worse than before, right? Before we were 10, 15% off. Now we're 50% off. And that's because the more we increase this these unrolling parameters, the less iterations we had to do. That's good. But also the more useless iterations we got compared to useful operations, which is why I spent all this time talking about loops relative to each other, and why it's important to keep in mind to keep these loops large. And there are now a bunch of tricks we can use to fix this. But first, let me go through the last problem we have to deal with. I might have to move a little faster now. Let's see. Okay. So now we did all this juicy unrolling. So the last issue we have to deal with is fan out. And this is another important thing to keep in mind, which is not directly obvious in all the stuff I've showed you, because what I just showed you is in principle good enough. Great, we can scale up to the full FPGA, use all these juicy resources, get all this parallelism. But there is an additional issue, because what I did was essentially this. I took a bunch of operations, I unrolled them in 2 different dimensions at the same time. So each of these would read from a separate value of A, but all of them would need the value of B that we gave in. So we would take this B and broadcast it to every piece of this circuit so that it could be reused. And the thing is, because of programming hardware, and this is an unrolled loop, these essentially correspond to physical connections on our chip. So all of these will now, when we actually synthesize this for hardware, mean that from some central point, we need to take this B and spread it all over the chip to all the locations that it's needed. And for some small amount, this is fine. But if we're now talking about going to a depth of 1,000, of 2,000, we're essentially saying to our circuit, take it from this point and spread it out over the device to 2,000 different places. And if you have a very smart compiler, it might be able to do some cool distribution tree or whatever. But this is not particularly simple because the schedule of the pipeline still needs to be maintained. So what often happens in practice is that it will really just try to fan this out to everywhere, and that is not scalable. So you would have a fan out issue here. And this is where all the talk about processing elements now becomes relevant. So we introduced all this parallelism, but now we also need to make this into something that can realistically turn into hardware. So how can we do that? Let's go back to thinking about processing elements. So what we could do is say each of these buffered values of A can now map to a processing element. It could also be multiple values of A, but at some kind of granularity, we need to map to processing elements. And what we then do is the accesses from memory need to still be there, but we don't want every processing element to read from memory because, again, fan out. If you had to access A and B from 1,000 different places on your chip, this would be a mess in cables essentially going all over your chip. So what we can do instead is we can be a little clever about it and say we have a processing element, just like the stencil example before, that reads in the values from memory and then passes them along. And it's slightly less obvious how this works now because before it was sort of natural to the problem that a stencil processes the value and gives its output. Now it's not quite as obvious because now we have to pass along values that we didn't change, but someone else also needs them. But it's not fundamentally different. We basically just want to go away from having this fan out to having something can be sort of pass along the chip. And these are now streams. And that is not useful because each of these processing elements become independently scheduled. And most importantly, the connection between one processing element and the next becomes a constant number. So processing element 0 and processing element 1 are only connected by a constant number of processing elements. Maybe it's 3, maybe of streams, sorry. Maybe it's 3, maybe it's 6, but it's constant, which means that if we start turning our knobs and increasing parallelism, we don't explode the number of things that need to be routed to the same place, which is the critical thing here. So we keep doing this to some n. A and B only access at the very head of this, and then we're left with only local communication. So no fan out that needs to go anywhere. And this whole thing will now be this global pipeline that I talked about a lot. So this whole thing, we can still schedule that as being a single pipeline that has all these juicy pipeline characteristics that we want so much. And this sort of architecture is what you will often hear to refer to as a systolic array. Honestly, systolic array terminology has no strict definition. Some would say this is not because A and B, for example, are not changed before they're passed along, and etc. But just keep in mind that when people talk about systolic arrays, this is typically the kind of thing they're thinking about, where you essentially scale up your parallelism by instantiating usually identical or almost identical processing elements in sequence. It can also be more than one dimensional, but we'll stick with 1D for this. So this is implemented in example 6. I will only look at this very briefly because essentially it's the same thing as before, but with streams shoved in. But I will just show you because I think it's nice to show you what this ends up looking like, because what the point we're at now is pretty much a fully optimized FPGA code. There are some small tweaks we can still do, but this is essentially what we need in terms of techniques. So same code as before. We have these unrolled loops, we have the vectorization, we have all this good stuff. We've replaced the interfaces with streams. So I'm not going to go into great detail with the streaming pattern here, but essentially we're taking in the values from memory, passing them along to the following processing elements, and passing along the results. And then at the very end, the result can then be written back to memory once it reaches the one processing element that needs to be connected to memory. The rest of the code is the same. The A buffer is now back to being just a single element because we essentially took this depth unrolling parameter and we hoisted it out again and said the depth parameter now becomes processing elements like with the stencil thing instead of being just an array inside of each of these kernels. So if we go down to our global function here, there's a bunch more code. You can look at it yourself if you want to see all the details. But this will now look like the processing element example we have for the stencils, where we have basically functions at the head that are reading A and B, a function at the tail that is writing C, and then a parametrically unrolled parallel unrolled loop here that will instantiate all of these individual processing elements that will now be connected in sequence. And the actual computations that will be done are the same as before. The only thing is we have to be a little careful now with the iteration space, make sure we pass along the right values at the right time and don't get stuck anywhere. The good thing is this is quite easy to simulate, so we just have to run this in simulation mode, make sure that we produce all the right elements that need to be consumed at a later stage, and then essentially we have our systolic array going on here. The one other thing I also added here is a tiling layer. So this is also just to show that we don't need to buffer the full width of the matrix. In this case, I only buffered the tile size of some TM here, which we then use as an inner tile size here to split up our matrix. So this would mean that we can now also support arbitrarily large matrices, even with a runtime known size. But I invite you to look at the details of this yourself if you're interested. The important thing I want to point out here is that this is basically everything you need to reach maximum performance on an FPGA. Of course, there are lots of little tricks and things you can improve and so on, but the fundamental concepts are these that we've covered so far. And that's sort of what I want to what I want to end with here. So let me jump back to the slides. All right. So like I said, these concepts are basic enough to fully utilize an FPGA. So there are a few optimization potentials left. We actually have like a fully optimized gem example on GitHub, which is also, I believe it is linked either from the slides or from the example page, where you can see really every last optimization applied. Of course, it starts getting into more messy code, but I just briefly want to tell you what those remaining things are. We can do some, like the initialization trick, we can absorb the writing of C, so it doesn't have to be this extra loop. We can do double buffering, so we don't have to first read all of the values of A before streaming B. We can just merge those two loops, essentially fuse the two loops, so we start buffering stuff while we're still computing stuff. We can pipeline this initialization phase so that the outer loop essentially just becomes part of the main pipeline. Again, like I talked about, when you have this outer time loop that is becomes multiplicative with the latencies of the innermost loop. If we're clever enough, we can also absorb the outer loops into the inner loops. It makes the code sort of increasingly uglier, but that can push us towards the situation where we really have the perfect pipeline behavior with just the latency plus the product of the dimensions. Yeah, here's the link. So for really the full-blown everything optimized, etc., there's an example code here. This is also linked from the paper. So if you look at the survey paper, we have these examples as publicly available repositories. So you can go look at it and play with it yourself and build it for your own FPGA if you're interested. So a summary of all the stuff I talked about. One of the first issues we dealt with was interface contention. So when you're dealing with having to, in a single cycle, access the same thing multiple times, we basically had to explicitly insert fast memory in order to not read the memory multiple times in the same cycle. So we had the situation where we had to read the same array twice, and we essentially stuck in these registers so we could propagate the value during runtime and only read the array once. Then we had the whole parallelism aspect. So we're doing HPC, parallelism is cool. And we had these two dimensions to unroll, but most importantly, the vertical dimension. So in order to really squeeze out performance out of FPGAs, we have to find this temporal locality and then figure out a way how to parametrically unroll that dimension to increase our parallelism as much as we need to utilize all the hardware we have available. Then we had this loop carry dependency. So this very common scenario of having accumulations that depend on some accumulation variable and then prevent you from pipelining the loop because you have a loop carried dependency where you need the result of the previous cycle to compute the next. So we could transpose entirely or transpose in a tiled way to basically move the reduction dimension out of the innermost loop and thus make this problem go away. And every scenario you have like this is always solved with some form of loop reordering, typically involving some strip mining in one way or another. And then finally, we had this fan out thing. So for this, we really wanted to design with this processing element mentality in mind. So when we really start scaling up parallelism, then at least the first solution is that you need to find a way to partition this into a way where you don't have this fan out problem. And this is always possible. It's just a question of how natural this. So for the stencil, it's a very natural way of programming it. For the matrix multiplication, it's slightly more awkward, but nothing more than what a little clever indexing can solve for you. All right, so that's the full summary. So thanks for sticking around if you're still here. I'm gonna stick around for the next 20 minutes for the full time that's scheduled to us and answer any questions you might have. But please ask questions that you still have. And otherwise, my email address is here, and I'm always interested in. I have no voice left. I'm always interested in cool applications of FPGAs and improving programmer productivity, which is what we care a lot about in our lab. And I recommend checking out the paper if you get into performance optimizations. All the techniques I talked about are there, and also in more detail. And there are cheat sheets in there to say, if I have this problem, I can solve it in this way, and so on. Otherwise, thank you for staying around. And if you're half as exhausted as I am, then you probably need to go get a coffee soon. But like I said, I will stick around a little bit and answer any questions you might have. If you're lucky, I might even have backup slides for some of them. So what do we have here? Let me just have a drink. So one question was, when implementing multiple kernels, are these tools smart enough to reuse some of the common logic between kernels? No, is the short answer. The long answer is you don't necessarily want that. So because of the issues I talked about with interface contention, most of the time you need the parallelism anyway. So you have to replicate things because otherwise you don't have enough physical interfaces available to you to actually do all this stuff in parallel. There are scenarios where you can reuse expensive components. For example, if you have a very expensive computation, but it's done very seldomly, there are ways to do this. Either you can, in the Xilinx flow, you can do this by essentially preventing stuff from being inlined, and then it has to be in the same code section, stuff like that. But then you can make it reuse it, which will of course mean that you cannot pipeline multiple access to that at the same time. And the other way of doing it is instantiating it as a separate processing element and then sending data when you need it and getting back results when you need it. And because it's asynchronous, you can tolerate having to wait some amount of cycles before your result comes back. So they can reuse stuff, but I would say in HPC context, it's actually not very often that you want that. Of course, I don't know every possible use case, but at least if the kind of stuff I've bumped into for HPC, the reuse that you have is usually always explicit, not implicitly reusing stuff. So another question is, does statement order matter in HLS data flow scope? No, it does not. The data flow scope basically just takes every function call in there, instantiates it as a different processing element, and links them together. It's not entirely true because, like I mentioned, the Xilinx tools natively don't do this very cleverly, so they will actually execute every function one by one. In that case, it does matter because you cannot read stuff before you cannot consume stuff before you've produced it. But I would recommend that in practice you simulate it using these macros that I just showed you, because then you will get the actual hardware behavior. And in that situation, no, it does not matter. They will actually run in parallel. Let me see here. Are there any special case where we have to synthesize multiple kernels at the same time? So I'm not entirely sure what you mean by synthesize at the same time. Depends on whether you mean synthesize as in compile them at the same time, or what if you mean that there's some reason why we want to semantically split the same thing into multiple kernels. In terms of synthesizing multiple kernels at the same time, I mean, this depends on how you wrote your program. The way Xilinx does this processing element abstraction, the sort of natural way to write it is everything is one big lump. You have your top level function and you synthesize all of that at the same time. In the Intel world, each of your processing elements are separate kernels, but they also just compile this as one big lump. However, both tool flows do allow you to compile kernels separately and then later link them together. It's just a bit less intuitive how to do this because they need to be linked together at compile time, right? You cannot dynamically say this kernel communicates with that kernel because they have physical hardware interfaces on the chip. So that means that you need to provide some configuration file where you say that interface of kernel A should be connected to that interface of kernel B, and then link that together when you're actually building the kernel. And otherwise, splitting stuff into multiple kernels, that's usually happens because of the scenario I just told you, where you want to schedule things differently, but otherwise there's no particular benefit in doing this. Let me know if I didn't understand the question exactly, and I can try to clarify. Let's see. I'll show you one other thing. So there were some questions about the materials. So on the website of our lab, if you go to the SPCL website, spcl.inf.ethz.ch, if you just search for SPCL lab on Google, it should come up. Then under teaching, there is a website for the tutorial. And this site is at least attempted to be kept up to date with the newest versions of the slides, links to the code, links to the tools that we use, link to the virtual machine, link to the paper, all the stuff that I mentioned throughout the tutorial. So this is sort of the easiest one-stop solution for all the material that's related to this tutorial. So if there's anything you're missing or you didn't get the handout materials, anything like that is all available on our website. Also completely independently of SC, it's all here. So feel free to check that out if you're missing something. So this is spcl.inf.ethz.ch. Okay. So question here is, I'm interested in FPGA programmability for network application. Cisco Catalyst. I don't know Cisco Catalyst, so I can't answer that in great detail. I haven't done too much networking stuff myself. But it's an excellent application of FPGAs. So as you might know, FPGAs in the context of HPC is kind of a funny child because it's been a hype topic for many years now, but no one really manages to do something cool with them in sort of a pure HPC sense. And there are many reasons for that, which I'm happy to talk about if you're interested. But for networking, FPGAs are employed in the real world with great success. There's an excellent application because you can guarantee line rate essentially. So if you have a stream of data coming in over Ethernet, over PCIe, or whatever you might get it from, you can write a kernel where you're guaranteed that you can process all of that at line rate. And in network applications, for example, this is bump into wire abstraction, where if you have a network stream, it can be very useful to stick an FPGA on your network stream and do processing on the fly. You can apply buzzwords such as near network or in network computing, or near memory computing in situations where you use the FPGAs as a database. So at ETH, there's been a lot of research in FPGAs for database acceleration, and you can do lots of cool stuff there by basically using the FPGA memory as a database and doing processing while you're doing lookups and stuff like that. And HLS can absolutely be applied to this. There are situations where you might want to use HDL for some of the latency sensitive stuff, but there's no reason why you cannot use HLS for some of these use cases as well. So anything networking related is definitely a very good use case of high-level synthesis tools. Yes, and thank you for linking the URL that I tried to spell out verbally. That's probably a better idea. Thank you, Alexis. Okay, compiling at the same time. Well, so no. Okay, so then maybe I understand the question better. There's no reason to do that because if you actually want both of your kernels to be present on the FPGA at the same time, then you have to anyway do the compilation flow together. So if you think about it in terms of compiling and linking, actually that's how Xilinx has actually expressed their compilation process as a compilation and a linking process, which honestly makes absolutely no sense, but that's how they did it. Then the compilation phase is quite cheap, where you basically just take the C++ code, you translate it into some RTL, and 99% of the compilation time is the linking phase, which is basically taking all your code and fitting it onto the FPGA. And if you split your thing into multiple kernels, you can do the compilation step in parallel where you translate it into RTL, but all your time is spent in the actual mapping to the device anyway. So you wouldn't win anything by doing this. The only use case is if you actually want them as separate FPGA bit streams. So if you want to run one kernel, reconfigure the FPGA, and then run another kernel. And this is a super cool use case, except it's almost useless in practice because reconfiguration time on FPGAs is so slow right now. Xilinx FPGAs take in the order of seconds to reconfigure. So it's a very weird scenario where you would have a kernel that runs for so long that it makes sense to reconfigure it when it takes you seconds to reconfigure. I hope this gets better in the future. I know that there are some sort of hand-rolled reconfiguration tools that are faster when you only reconfigure a subset of the FPGA, but this is not easy to use in practice. So right now, I would not recommend ever doing on-the-fly reconfiguration on FPGA until the vendors improve the reconfiguration times, because it's honestly a disaster right now. Okay. All right. That seems to be all the questions for now. Yeah, I'll stick around a little bit. So I'll just monitor if there are more questions. For anyone who is interested, I will have a little fun slide I want to share with you of the FPGA development process. Again, very much, I am not affiliated with any vendor style of slide. If you have any further questions, just post them and I'll see them before we end. So I made this is actually a slide I made for internal use in our lab, just to sort of explain to my lab mates how FPGA development works, to give them an idea of what I'm struggling with in my daily research life. But so this is hand-drawn, completely qualitative, pulled out of my something graph, but I just give you a little idea of what hardware development is like compared to software development. So if you think about time progressed here as being development time, so the amount of time you spend writing your application, and the y-axis is how much performance you get out of your application, you can think about it in the following way. So this is your CPU/GPU development process. Essentially, you start somewhere, you find out I can add tiling, great, this gave me an extra performance boost. Then, okay, what can I do? I will tune the tile sizes a little bit. Maybe I didn't quite fit my cache well enough. Maybe there's some behavior I didn't manage. I get a little bump of extra performance. And then we have a long period where like, oh, now what? Okay, maybe I can come up with some extremely clever tiling scheme. I'm going to call it Johannes tiling. I'm going to publish a paper about it and have that published, and people will applaud my amazing, extremely complicated nested loop schedule, and then I get this tiny little 10% bump in performance. And after that, we can hire some more PhD students, and they can think about how else to tile this thing and come up with new clever ways to optimize this thing more. Hardware development, on the other hand, is my program doesn't work, and for the first half a year, okay, that's maybe a bit pessimistic. For the first 2 months, my program just doesn't work. It doesn't compile, or the results don't make any sense, or nothing makes sense anymore. And by the time I actually get it to work, my CPU buddy already has amazing performance, and he makes fun of me. All right, so this is the oh my god, it compiles stage. Stuff actually works now. And then there's this stage. So now I figured out, oh, here's my source of temporal locality. So now I can replicate my thing and get all this juicy parallelism that I was talking about. And then I get this huge bump in performance where suddenly I'm using, I don't know, 100 times more of my FPGA. Then here's the part where I figured out, okay, this does this fan out problem, but now I can add some processing elements to this. I can do this clever systolic array architecture, and then suddenly I get another huge bump in performance. And the development process sort of looks like this, that you usually start from something that doesn't work at all. Then you get something very slow. But then when you actually crack each of these problems, you immediately see this benefit because there's no weird instrumentation. There are no implicit cache hierarchies, but rather you can explicitly target these things you want to target. And if you're lucky, you might actually end up in the rightmost step here and get to a point where you have a cool, fast design. But it's sort of a whole different roller coaster in terms of the performance you get out of your kernel. And then in the end, we can do small things, tuning the frequency, moving to HDL, for example, break out our Verilog and see what we can tweak and see if we can go from 300 to 350 megahertz and stuff like this. So yeah, I just want to show you this little slide, maybe also to prepare you mentally if you want to do any FPGA development of your own, that there can be a long path to the point where you have anything remotely useful, but it's very satisfying when you hit each of these bumps because the bumps are huge. So the frustration of programming FPGAs is also sort of the cool thing about programming FPGAs is that it's very satisfying when you hit one of these points. Okay. So that is all I'm going to blabber about for today. So again, thanks everyone for showing up. And I think that was all the questions. And like I said, feel free to reach out. I'm happy to answer any further questions you might have. And thank you very much for spending your morning or evening with me, depending on where you are geographically. And I wish you a good remaining SC. Thank you.